Okay, good morning, everybody. Welcome to the course. First, before starting, I want to say that I'm going to share here in the chat of Zoom the connection to the invite to the Slack channel. If somebody hasn't logged in, maybe it's better because I think it gives a better experience to discuss and ask questions. And so let's go a bit about a quick overview about the training. So here in the general channel of Slack, we put the agenda. So for today we're going to start with introductory topics, and we're going to see some concepts and of Python that are relevant for the training, and then we're going to move to learn a bit or refresh a bit NumPy and see a bit how the vectorization works, and finally we're going to learn a bit how to profile, very simple things for profiling in Python. And at some point during the morning we will have like 15 minutes break. It should be around 10:30 or so. Then we have the lunch break, and in the afternoon we have the session, we call it Extending Python, that you're going to have with Theophilus. You're going to see how to optimize code using Cython, and later we're going to see how to write bindings for Fortran and for C. And then tomorrow, all the day, you will be with Theo, and it's mostly going to be about using GPUs in Python. And on Friday, we're going to do just only morning, and we're going to see how to parallelize work in Python and how to distribute and scale over PC-Dynamo, so how to use multiple nodes. And so if you have questions of any kind, just please type it on Slack, and we're going to try to reply the one of us that are not talking, or time to time we're going to stop and try to look at the chat. We can do this in this general channel. And here this information here is pinned, so if I think somewhere in the chat here, you can go to pin messages and you can always find it, even if we start writing here. Okay, first, most of the things we're going to do it using Jupyter Lab at CSCS. So please go to this this link and log in using the credentials that we give you, the HCK account. And there, when you log in, you will find a welcome page to launch Jupyter. And so please put 8 hours in duration, because if you put less, you will stop mid tutorial or something. So with 8 hours, it will cover the whole day. And then you can click advanced reservation, and in the left you will find, advanced options, and in the left you will find something called advanced reservation, and please put course day 1. If you're already logged in, not logged in, sorry, if you already have the Jupyter Lab running, don't close it and do it, just stay like that. But if not, put this one, because you will get you will use the reservation for the course, and it will be quicker to log in. And then, so when you have the 8 hours and the course day in the reservation, day 1 in the reservation, just launch Jupyter, the red button, and then you will end up in Jupyter Lab. And just for tomorrow, I will say it again, but the reservation will be course day 2 and course day 3. Okay.
I'm sorry for the interruption. All the other default settings and the advanced options we should leave. So like Jupyter Lab version 1.2.16 or.
Yeah. Don't everything else as default. Just change the ones I mentioned here.
Okay, thank you.
Okay. Yeah.
Rafael, can you share also so that we can see the browser?
No, the problem is that I am already connected. I already have my Jupyter, and
Okay.
You cannot see that page anymore. So then, independent of that, you can. We're going to use a Python installation that we prepare for the course that has all the Python packages that we'll need, and you can. You have to create it, and for that, just run this thing that I'm marking here. Just copy and paste this thing in your open terminal on Dyn, and just copy and paste it on Dyn, and that will create the kernel for you. And then nothing that you have to do anything, just doing this, and then later you will have the kernel available on Jupyter. I will show you afterwards how to select it. But by now, just run this thing. And this also will create in your home folder a link to your Scratch, because Jupyter, you cannot change file systems to another mount point on Jupyter. You will be always on home. So we're going to work on Scratch. So this one, I will create a same link in Scratch, and you will see it in the file browser of Jupyter. So you can navigate to Scratch. Okay. So just copy and paste this thing on that. So the repository is this one.
Rafael, you are sharing only your slides.
Oh, that's true. I'm sorry. Yeah. Well, yeah, maybe I can just stop the share and share the stop share. Yeah, thank you, Ted. Yeah, sorry. So this one is what you have to run on Pysdyn. Okay. Then the repository, you have it here. There you can find the slides and all the examples. You can clone it already if you want, but please clone it on Scratch. So you just go in a terminal to Pysdyn and go to Scratch in your course account and clone it using this command, because there are some exercises, some tutorials that are not going to work if they are not in Scratch. And just please remember that these student accounts, they will be valid until Friday. So after Friday, everything that is there is going to be deleted. So please always remember, if you change something after the course finishes, you should copy to your Pysdyn account, or you copy locally to your computer. Okay.
Rafael, for all this, we need to log in under this new course account, right?
Yes.
And isn't that course account the same for everybody?
No.
HCK06?
No, this is yours. Mine is 01, and somebody else is another different number. Okay. And the webinar link for tomorrow, because you can find it here too. Okay, so I think I can stop this, and we can start. Stop share. Okay, my presentation is in full screen.
Yes.
Thank you. Okay, so then now we can start with the actual content. So here we are going to look a bit better to look quick to not better look quick to some concepts of Python that we're going to be using through the course. So we're going to see what is reference counting, garbage collection, and what is the global interpreted log that you may also know it as GIL. So first thing is Python is always, or used to be, associated to just scripting and read a file and change something quickly, and we still use it for that. But for already many years, Python is always been every time more present in HPC. And right now there are a lot of any kind of packages that you can imagine for doing HPC. Today we're going to see some, in this course we're going to see only some of them, but every day there is something new if you follow this kind of community. And one of the things that make it useful for HPC is first that Python is very flexible and all the operations can be overloaded very easily. That is, for instance, if you have seen the old TensorFlow, TensorFlow 1, that you wrote it was Python, but it didn't feel like Python at all because you sum two variables and you didn't get a result. You just created a graph, and nothing really. It really felt like a new programming language, and this is because it's very easy to change how Python works, and this is something very important. And the most important is that it's very simple to bind it to languages like C and Fortran, which is where you can do really let's say the good stuff. You can do sophisticated programming. You can code things specific for a specific CPUs, specific architectures. You have access to the GPU, to NPI communication, and everything. And actually, in Python, when you run it, in general, use something for numerical computing, you will have the Python program. The Python is going to run, but anytime that you have something that is CPU intensive, that you need computer power, in general, you will call behind the scenes as C code. Then this C code is going to execute, and then Python is going to continue, and you will call something else, and then you may create processes, or you may create different threads and continue. And in general, this is more or less how Python works in practice. You don't see it because everything is hidden behind Python wrapped functions, but it's something like this. Okay, so now saying that, we can start seeing the topics. The first one is reference counting and garbage collection. So let's see this one through a very simple example. Let's say that we have a script that it starts with a code like this. You create a NumPy random array, and you pass it to the variable a. This one is going to create a block of memory, and in this block of memory, Python is going to assign a reference counting, which is how many times this block of memory has been referenced. This means how many variables are pointing to this block of memory. So when you do this, you can get reference 1, and this is Python has its count, and then let's say that you do b equal a transposed. That a transposed doesn't change the memory; it just changes the way the memory is read. We're going to learn it later, but you pass it to b, so b is going to be looking also to this memory. Now Python says, okay, the reference of this memory is 2, and this is how the reference counting works. And if you create your script continues, you create two other things. They are going to be allocated afterwards with reference 1 and 1. And now let's say that you delete this one, C. When you delete C, what happens is that the reference of this memory that C was pointing at is marked as 0. So before was 1, and now nobody is referencing it because C doesn't exist anymore. And this is marked as a reference 0. And there is a second process that is called garbage collection, that are 6 cycles that go through your program. And Python will be checking, the garbage collector will be checking which memory has a reference 0. And when he finds a memory with reference 0, he will mark it as free. And now Python knows that it can use this memory because it's free. Of course, you can use the same thing if the same thing happens if you point C, this variable, to somewhere else. So not only if you delete it, now C is not pointing to here anymore, it's pointing to where the 1 is stored. And this also will count the reference as 0. And this space, since it's not going to be referenced, is going to be marked as free. Now, if your script continues and you create another variable, but this array is larger than m, it won't fit here. It won't fit here. So it will be allocated at the end, and this space is going just to be there. The only way this space might be allocated is if you create something that fits there. Okay. And this is very important. This is how the garbage collection works. And in Python in general, we don't have to think about it because all this is automatically. But when we are dealing with large data, not large data in the sense of data science, but big arrays and sizes that can really use up all the memory, we have to pay attention. With this. For instance, in cases like this one, you know that you created B, but B is not really creating new memory, and in this one that you created new memory. So it's important to be aware of these kind of things. The second concept is the GIL, the global interpreted lock. So the global interpreted lock, the GIL is a lock, and a lock in computer science is called to a mechanism to enforce limits for us accessing resources in environments where there are many threads. The problem here is why we need a lock. The problem here is when, since you have the garbage collector and the reference counting, if you have multiple threads and the threads have shared memory, it can happen that in one thread you do something like, I don't know, you delete something or you decrease the number of reference, and in the other one you increase it or you do the same. But it can happen that both threads go to change the reference of a space of memory, and they can corrupt it because one is not the ordering in which the things happens is not determining things. The threads are running at the same time. So in this case, if you have the global interpreter, if you have the garbage collection and the reference counting, you cannot have multi-threads. So if you have multi-threads, you will end up in corruption. And this can, and if the reference is corrupted, what can happen is that some memory that is supposed to be freed is not freed, or memory that is not supposed to be freed is deleted. It's marked as a reference 0 and it's freed, and then you can get you can lose data, or you can create your program can crash, or you can memory leaks, or you can read different. It really can create a huge problem, and for that you need Python needs the GIL. And the idea is that this is a mechanism to enforce that not two threads are running at the same time and are not accessing the memory at the same time. And to understand how this works, you can think in a game that the kids play with in a school. That imagine that so all the kids, they have to say a story. So imagine that the kids are the threads and the story is the work that the thread is going to do. All the kids have to say a story, but they cannot talk all at the same time because otherwise it's a mess. Then what the teacher does is it gives something, a toy, to the kids. So only one toy to one of the kids, and the kids that acquire this toy can can talk, and the rest cannot talk. They have to be in silence. To talk, to another kid to talk, they have to wait for another kid to finish with the toy. So he says whatever he wants to say. It will be a part of the story, and give it to another kid. And like that, all at the end, all the story is going to be done, but not at the same time. And this is exactly how the logs work. The logs, they have two methods: acquire and release. Acquire would be like getting the toy. So sometimes you can in Python you may hear acquire the log or release the log, and this means acquire the log means, okay, I have the permission now to run, access the memory, and do whatever I need to do. And release is I finished doing what I was doing, and now some other threads can go and do their job. Okay, and I think this is something that how Python, in particular CPython, which is a Python implementation, how Python is implemented. And I can show you an example now. I will stop here and go to Jupyter. Would it be bigger? No, not big. So here we're going to do an example to simulate how what happens without log and what happens when you have a log. And for that, we're going to use the threading module of Python. So we have these two functions. That's what they do is they have they loop, so they print this thing many times, so 10 times, and to print they loop over this list and print every word. And this one does the same. So one is going to be green and the other one is going to be red. And here we are not using a log, and we can see that if when we run this thread, I'm sorry, I think I skipped a very important part of the explanation. So we put these two functions in different threads. So we have in thread 1 is going to run function 1, and in thread 2 is going to run function 2. So now we start the threads and we stop the threads. So when we run it, we see that since it is not printing print the whole thing, the function, it's just looping, the one thread interferes with the other one in the std out. That would be the resource in this case, no? And this happens because we have two threads and they are interfering with each other, and we don't have log. And if in this case it's not that important, but imagine that we're doing a calculation like this, and one thread is changing one variable that is used in the other thread, and everything is going to be messed up. Okay. What Python does to prevent this thing from happening is to use a log. So now we're going to use the same threading module, and we're going to create a log. So a log is just this class that it has the acquire and the release methods. So now inside of this loop, that is what is breaking here, right? Inside of this loop, outside of this loop, inside of the main loop, we are going to wrap it with the acquire and release. And this, the only thing that you have to understand that it means is that when the two threads start, so the first one that arrive to this line, because there is always a small delay between the threads. The first one arrives to this line is going to lock out the other thread, and it's going to run. For instance, if this one arrives first, starts first, gets the lock, acquires the lock first, it's going to run, and it's going to lock out this one. So this one cannot run, the other thread. And when releases, the loop is going to continue, and the first one that arrives, that acquires first the lock, is going to lock out the next one, and so on. So we can run now, and this happens. So now there is no interference between the two threads. And notice here that there is never interference. There is the word hello from. They are never broken. It's just what is broken is this loop here, because the print itself in Python is implemented like this with the lock. So you won't get the print of Python broken in half. Okay, using multiple threads. So I will have a look to the chat. I move it here to the chat to see if there are questions. Okay. Okay. So, and this is how Python itself is implemented. Every function has this is wrapped by a lock. So you cannot have multiple threads in Python. If you want, if you need to do multi-threaded in Python, you have to go to the Python API, and if you want to create a new function, and you have to modify this behavior. You have to make it release the lock the first, and then do the multi-threading thing that you want, and then of course acquire to continue the flow of Python. So I go back to the presentation. Okay, so that's it. How the logs work in general. In Python, there are two different kind of implementations of log. One is CPU bound. That this is for functions that do something using the CPU intensive. In general, any kind of operation, changing memory, I don't know, something that really needs the CPU. And these ones, they are implemented exactly as we saw. They acquire the lock, and they release the lock always. And there is another kind that's called IO bound, that are called for the OS, that they can be saved in a file that takes time, or it can be the sleep function, the time.sleep. So these ones are implemented release lock, and they do the things and then acquire the lock. So these kind of functions, you can run them actually multi-thread. This one you can't. Okay. In Python, in NumPy, for sure you know that in NumPy many functions are multi-threaded. If you go to top, you will see that you have many threads using running your code. But here, if you look you go to the source of NumPy, you may see this this directive here. No, not directive. These macros, I guess they are. NumPy loop begin threads and NumPy loop end threads, and inside they are wrapping the content of the function. And this is how NumPy releases the thread, the lock to do multi-threaded operations. Okay. And now quickly, since you are users of PySdint, I want to talk to you about the Python distribution that we use on PySdint. So the first one, the more common, is Cray Python. That one comes with the Cray software stack. that you select it like this, module load create Python version. And this is pretty much Python, like any other Python that you can have in your computer. The main difference is that NumPy uses as backend something called libsci, which is a numerical library from Cray. So when you do a NumPy dot, or I don't know, any kind of operation of linear algebra, FFTW or something, you may use functions from here. Okay, and in your computer you may use BLAS. That is a difference, and that's it pretty much. For the rest, is more or less similar to any other Python. With it, you can use the libraries installed in Cray. You can use module load py extensions. This is an extension of other modules, that common use modules that you can find on page9 for Python. And you can use TensorFlow, and you can install things in your home folder using pip install ---- user, or you can create a virtual environment, etc. Some other packages like PyTorch, for instance, we give it with Anaconda, which gives a different, it's another distribution of Python. And in particular, we use Miniconda. That Miniconda, when you install it, you get just a bare Python installation. You don't get like Anaconda, hundreds of libraries that you may or may not use. This one, if you want it, you have to install it yourself. Although it's right now, I don't think it's necessary. It's not really necessary. You can really go with the Cray Python. And this one, the main difference to Cray Python is that the backend, instead of libsci from Cray, it uses MKL, which is Intel's math library. And Anaconda, when you install it, you not only install Python, but you install many other libraries that Python needs, that otherwise you would use from the system, but Conda brings everything self-contained. I think outside, Conda would only need the drivers. The rest, it already brings it. And you can install things with Conda install. There are different channels to install, or you can install pip, like with pip install, like you would do normally. And just as information, pip install, when you install things from pip, you are installing it actually from PyPy, which is a Python package repository. And the binaries there are compiled for generic architectures, like for Intel, and but not so in general, no? But sometimes you need in HPC in particular, you need to build. You may need to build from sources some packages that. So in general, if you have something that is compute intensive, you may have a look first to the recommendations to how to install it, because not always pip install is the best solution. Okay? And that's it for this part. Now we can go, and we're going to start seeing NumPy. So I'm going to stop here. Oops. Okay, So now we're going to start with NumPy. There will be most of the morning session. And what we're going to do is we're going to see some basics of NumPy, and then we're going to implement some distance matrices using different approaches, and then we're going to continue this for today in the afternoon, tomorrow with Theo and the GPUs, and even on the scaling on Friday. So we're going to see different options, how to do it in Fortran, how to do it in C, of course, a lot in Python, how to use it in Dask. So it is going to be a continuation. So if you download this now from the repository, you may see other things, but they are going to come on Friday. Okay? So NumPy is a Python library that gives the primary support for arrays, matrices operation, and numerical things in general in NumPy. Sorry, in Python. It has the NumPy array, which is the center of the NumPy ecosystem, and this is a n-dimensional array. This is kind of a C object, and all the operations and everything goes around this array in NumPy. So besides this, it brings many sophisticated functions, also written in C most of the time. It has linear algebra, Fourier transform, random number capabilities. It brings also a program that's called F2Py that you can use it to create Fortran bindings for Python, and it's very simple to use. We're going to learn it in the afternoon, and it's compatible with C, which means from C you can access very easily the memory used by NumPy, and because they have the same, it's saved in the same kind of order that C does. So together with NumPy, there is SciPy, which is you can see it as an extension of NumPy, which brings many more other numerical routines to work also with the NumPy array. And then you have optimization, integration, interpolation, more linear algebra, statistics, many things. It's a huge library. And again, it's meant to be used together with NumPy. Okay, let's see some examples. So in NumPy, the array that I mentioned before, when you create it, it looks something like this. This is a Python list that you make it a NumPy array, and in this case we selected to have int 8 because of an example that I'm going to show later, and you get something like this. Is in this case you see in Python it will be a 3x3 matrix of this D type, but in memory what you have is a block of memory that is a C block of memory, just continuous. It's not there is no, I put it here square, but it's like, imagine that just a continuous of numbers. And here, if I select with colors, here we have the 0, then the 1, the 2, the 3, all the numbers one after the other one, like you would have in a C array when you create it. So this thing alone, it doesn't have any notion of shape or size or how long, how is the size of each element. So the NumPy array has also something called metadata besides this thing, and the metadata, it writes the shape. The strides that we're going to see later is the way how NumPy is going to read this memory, the type, the dimensions, and with all these parameters here, you can interpret, and also Python can interpret this as a matrix or the things that are used to see in Python. Okay, so this memory in NumPy is called data buffer, This is called metadata, as I said. This is stored in C order, so row major. By default, you can also change it. And all the items, they have only one data type. You won't have an array that is int 8 and int 16 and int 64. All the elements will have the same type. So let's say that we have this memory, this data buffer. Now I put it in decimals to make it easy to see, but it will be the same. It will be binaries. So if you have this data buffer and you give some metadata, you can have some interpretability in NumPy. So here we have a strides that we say this for 1. We have shape. So now we know that this is a 4x4 matrix. And int 8, now we know that every element, it will be 8 bits. Okay? So this one, these two are clear what they are, but the strides is a bit not too intuitive to see from only this definition. So the strides will tell you what is the difference between this matrix and the transpose. So if you see, this one is for 1 and this one is 1 4. So the strides will tell you will tell NumPy, not you actually, will tell NumPy how to read this memory. For instance, in this case, strides 1 4, it means that in the columns, to go from this element to the next element, so to move in the column, you will move only 1 byte. So here is not bit, it's byte. So if you give the element this one 1.0, NumPy knows that this one has to move 1 byte here. It will be this element here. Okay, this part of the memory. And same for this one 4. It will have to move to go from 0 to 4 to the second element in a row. It has to move 4 bytes. So from here to here, NumPy will look for the value at this point. Okay, and like this, you don't need, if you do a transpose or in many other cases a reshape or something, you don't need to change the memory. You just change the metadata, which is a simple, it's an easier transformation in the memory, so you can do faster things. Okay, so now if we do the transpose, so now it changed for 1, and here it changed from 048 to 0123. So now in this direction, you move 4 bytes. So if you want this value, you have to go 4 bytes. And if you want this value, you have to go 1 byte. And again, I said you have to go, but it's NumPy. You don't do anything now. So NumPy does it for you. NumPy goes 1 byte or 4 bytes. Okay. And the formula to get when you say x, your array in 0 1 on the index and the indices, NumPy transform it like this. So it will be strides in 0 times the index that you give times plus strides in 1 times the index that you give. And that gives the position here for a given per A1, A2 indices. Okay. And now we can go to the notebooks. I hope all of you already managed to get it. And we're going to do a very simple exercise. It will be like 5 minutes to try to understand these arrays. And we are going also to see how operations that you have to try to understand if there is a metadata modification or if the data buffer is copied again, it's transformed. So I'm going to stop here and go to the notebook.
Rafael?
Yes.
Can you repeat on how to get all the stuff for the course? Because I missed you on that.
Do you log in on the Slack channel?
On the Slack channel?
Yes.
Yeah.
So if you go to general, in the general channel in the Slack workspace, if you go to the top of the comments, there is the session material for the course. Can you see it?
Where is it?
In the chat, in the left top, it says general, the general channel.
Yeah, like that.
Yeah, if you enter there, if you go to the top of all the comments that are there,
Yeah.
there is the agenda, then Jupyter CSCS, Jupyter kernel setup, and material for the course, and there you can find the repository.
Oh, the git clone command. Okay.
Yeah, okay. So I'm going to move to the Jupyter. Sure. Okay, now if you already clone the repository, it's a good moment to explain quickly a bit of what we're going to do here. So we are going to go to scratch in a terminal and clone the repository in the examples that sorry, in the like in the command that is given on general channel. And so you have all the examples here. You can go now to NumPy and open first NumPy arrays internals. I already have it open here. It's a 0, 1 and NumPy arrays internals. And here in this part of the notebook, I think you may have something that says Python 3. You have to change the kernel. And just select, just click on it, you get this pop-up, and just select Python HPC 2021. Okay, and now you will have here Python HPC 2021, and this is the kernel. Okay, is it clear? Okay, then so if all of us we are on this notebook here, so there is this array. This is the same that we have in the presentation. In this case, a 4x4, and if you put you can see the strides with x dot strides. In this case, 4.1. We already knew it, and there are some questions. And so you have different reshapes, and as you can see, like this, for instance, this one, the array you change it to a 2x8, and just as an exercise, let's try here to determine what is the stride, and you can use to x dot stride to check your answer. Okay, just create put here x dot stride and run it, and you will see the strides, and you see if your answer is fine. So there are different options here. Then we have this section here, metadata modification versus copying the data buffer. That there are these 3 situations, and you have to explain why the times are what they are, what you're going to see here when you run it. And you have to understand if there is a metadata modification or not, or the data buffer needed to be changed. Okay, so I will give you until 10, so 4 minutes, and then 10 we discuss. Okay. Okay, I'm back. Yeah. Just if some of you have problems to get the to navigate to the to the repository on the notebook. So you start here when you open your Jupyter Lab. You start on your home folder, and you will get, if you run this script that is mentioned on the general channel, you will get a scratch sim link here that you can click it, and then you
Rafael, too fast. How do I even get onto the home folder? All I see is this folder icon that you have /./Python HPC. I have just the slash. I don't know how to navigate in this Jupyter Lab.
Did you run the script to create the kernel and the symlink?
Where is it?
It's in the general channel. Jupyter kernel setup.
Under kernel in the menu.
No, sorry. It's in Slack in the general channel on Jupyter kernel setup. So you have agenda, Jupyter lab.css, and Jupyter kernel setup, and there you find the instructions. You run the script that is there on a terminal.
Ah, okay. Okay, I didn't do that.
Okay.
So there's a question from Felix that he's asking that he thinks that NPD shape would return a view most of the time and not changing the layout of the data in memory. Would this mean that the strides also not change in that case?
Yeah, sorry, if you can paste your questions in the general channel and on this chat, it would be better, because I'm not looking to this chat. Thank you, Theo. I thought NPD would return a view most of the time, not changing the layout of the data in memory. Would this mean that this strides also not change? Okay, I think better we discuss the notebook and we arrive to that question. Okay. So the first one we can check strides. So 8.1. Here. So, yeah, every one of them, it takes 1 byte, so it would be 8 bytes to move here and 1 to move here. This one is just a line of just a row, I guess, and then no, this one is a column, I would say. We do strides, and we get 16 1, right? Because if we print here, yes, this is a column of numbers, okay? And this one is int 16. So I have the same shape but different type. Is the same, it's very similar to the initial one that we did, but it's twice, because every change that you do, you, instead of 1 or 4 bytes, you move 8 bytes or 2 bytes. Okay. The notion of strides is, it's not important as a user, right? It's just I don't know, to try to understand how these things work, okay? But it's not in general things that you use in the day-to-day, unless you implement NumPy code or something that you do some implementation that you will need it, but in general, this is not something that you will do in the day-to-day. It's just more academic. Okay, so this one is simple, and we can move to the next one. So this one is it is important because of sometimes you could avoid doing things that will create more memory, or not even if you don't care about the memory, but in general changing the memory, copying memory is expensive and will make your scripts and your programs slow. So here we have this array, and it's 0, 1, so it's just 5 elements, and so we say y equal x ravel. The ravel, what it does is to flatten the array. In this case, it doesn't matter because it's already flattened, but and this array here, you say, okay, I'm going to change the 0 element, the first element, and put it 5, and then you print again x, and then you see that x changed. So this is in this case there is no change of memory, obviously. So both of them, they are looking at the same memory, and this is something that sometimes one has to be careful to do not change the memory of another array, because it may be connected to the same memory of other data in your program, and it can modify it. Okay. So if we continue here, so this one is pretty much the same. Now you have a big array, and so the first, all the operations are silly operations. They always do the same. This one will do a transpose, and they will do a ravel. The ravel that we know is to flatten the array. And we are going to measure the time. So this one is 243 nanoseconds. This one is going to do the same, but with the function flatten. So this one was nanoseconds. You see, this one is milliseconds, so it's slower. And here we're going to do the same with ravel, but we are going to ravel the transpose, not the array itself. Okay. And now this one, it takes even more than this one. No? And why is it so? Ravel we know already from here, right? That it doesn't change the memory. So it does a flattening, but the memory keeps being the same. And so in this case, it explains why it's so fast compared to the rest. So the next one, flatten, it changes the memory. So if you go to the documentation of flatten, it will change the memory, and you see it's slower. And this one finally, ravel, that we know that doesn't change the memory. Now it took even more time than this one, and that is because if you when you flatten the transpose of the array, you won't get let's say if it was this array, you won't get 0, 1, 2, 3, 4, 5. You will get 0, 4, 8, 12, 1, 5, and this operation, raveling a transpose, cannot be done just in terms of strides or in metadata in general. This operation requires changing the memory, so now it will create a new memory even if ravel doesn't do it. And this is how ravel works. It will do the operation as fast as possible, changing only metadata. But if you cannot do it, it will copy the memory. Okay. Does this mention your question, Felix? Sorry, solves your question? Well, I see that there is a discussion.
Yes, thank you. Thank you very much.
Okay, great.
I'm sorry, Rafael, I have a question. So about the time, first of all, what does this number of loops mean?
Well, I'm going to talk about this in the latest session,
Okay,
the last session in the night, in the morning. But just quickly, time it does it doesn't give you the time that this thing runs only once, but it will run the cell many times. The cell many times, and will take an average. That's why it gets here some value plus minus some error. But later today, just before lunch, we're going to learn how to change the number of loops that it does. Okay?
Okay, thanks. Another question: are you going to give us some guidance how we can optimize our code, basically? Because this seems quite ambiguous to me to know when I should ravel, when I should flatten. You know, the order of things. It seems a bit arbitrary to me what optimizes. So are you going to give us some pointers what we can do?
Yes, but I really don't know if they're going to be like a breakthrough, because I think, in my opinion, and of course, Theo, if you want to talk also, please. In my opinion, we're going to see in the next example is to try different solutions and profile. So we're with the profiling that we're going to learn later, and doing trying different solutions for the same things. Like in this case, if you go to Stack Overflow, maybe one day you find Ravel to do this, and maybe another day you find flatten. And if you don't keep, you just can put it there, and maybe can make your code faster if you use the one that you're not using. And the idea is, I think, is profile and try different solutions.
Okay,
but,
thanks a lot.
Yeah, this is kind of a dummy answer, but I think it's what the only thing you can do.
Yeah.
Okay, that's it. I hope this was clear. Again, this is more, but this part is important. The stride is more like academic, just to understand how it works and to see what is happening behind scenes. Okay, so I'm going to stop this notebook. I'm going to go back to the presentation. No. Okay. If you have questions of this later, it doesn't have to be that you can ask now and that's it. You can ask at any time on the chat. We can reply a bit later or something if it is outside of the current presentation. But just please, let's keep it this continuous discussion through the course. So the next topic in Python is something that we find very, very important, which is broadcasting. And this one you may use very often in your day-to-day NumPy coding. And broadcasting has to do in NumPy with operations, with arrays that have different shape. For instance, in this case, we are summing n by 1, but the 1 by n. No? And in this case, what is going to happen is that you're going to get an n by n matrix that it has all the combinations of all the elements of the sum of all the elements of this array. And how it works, or how you can understand it, is to this one, you are going to this column, to the column, to the row 1, you're going to sum all of these elements of the row. So you will have y0 here plus x0 plus x1 to xn, and then y1 and so on. No? Sum by all of them. And so this is a very simple case of broadcasting. And we're going to go back to the notebook. It wasn't really worth to change to the presentation, but and we're going to play a bit with this. And this one, it is a very important thing in NumPy. So now, please let's go to 02 broadcasting in the same folder. So here we're going to play and try to understand different cases of broadcasting. This is very important in NumPy, and the main point of doing broadcasting, why it is useful, is because in NumPy everything is meant to be done vectorially. If, for instance, in this case before that we saw the column vector summed by the row vector, if you would like to get this result that was the matrix of all the combinations, the sum of all the combinations, in NumPy you wouldn't do it with a for loop. You would do it with a vectorial operation that would be this one in this case. Okay. And this notebook, we are going just to play with this concept. So the idea is we're going to be building. We're going to start with the simple examples and make it very complex at the end. And this one we will use it in the third tutorial. That will be the matrix, distance matrix that I was talking at the beginning. So in this one, it's a very simple case. You have row vector plus scalar. It's the simplest case of a broadcasting operation. So in this case, every set, every element here is going to be summed by set. So you will get this thing here. Here I have no kernel. Maybe you have the same. Remember always to change to Python HPC 2021. Okay, so this is this case. We have NumPy arrange. This is a 1 to 0, 1, 2, 3, 4. We sum it by 1. We got 1, 2, 3, 4. All of them, they are summed. This is this case here. Okay, this is a very simple case of broadcasting. So let's move to something more important. So, which is creating new arrays dimension. So if you this array that we created here, you see the shape is 5. It's not 5, 1, or it's just 5. It should be like, let's say 5, 0, which means that's only one dimension. It doesn't have notion of row or column. It's like just one dimension. This array, doing with this kind of notation, bracket, colon, and NumPy a new axis, you can transform it and give new dimensions, and you can make it a 5-1 array. So this means this column is whatever the array has in this in the first dimension. So in the dimension 1 or the dimension 0, add a new axis. A new axis is a new dimension, and of course, if you have to, if I ask you to determine this changes memory or not, if you think a second about it, the answer would be no, right? Because to add new dimensions, you have to change the shape on the metadata. You don't need to change the memory itself. It's just how you're going to interpret this piece of memory of where the array is. Same thing here. You can create now, instead of a 5-1, a 1, 5. So this one, I don't know if it print is different, but probably yes. Ah, no, sorry. This one looks like this, and this one looks like this. So one is a vertical one, and the other one is a column, and the other one is a row vector. Okay. So what is the difference between the shapes? Well, we just saw it. And from what you have learned about NumPy initialize, does the operate? Oh, okay, sorry. We really went ahead and explained these two questions. But okay, probably you already know these things because so we mentioned that you would need the NumPy basic NumPy knowledge, and this is a pretty common thing that you may do normally. So and now let's consider something more complicated. So this one is the example that we saw before in the notebook. So if you have an array, in this case, that was this one initial, that we started with no shape, just 5 numbers, not shape, no, sorry, with 1 dimension, just 5 numbers, and let's say that you want to get all these combinations that we mentioned before. In this case, you have to do this sort of operation. You have to make it row and column arrays and sum them, and this is how NumPy is meant to use to this operation, for instance, no? to get all these combinations. And now, finally, for the next example, let's say that we have now not a 1, 5 and 5, 1, but we have an array of vectors, no, a matrix. No? So in every column or in every row, you will have a vector. So this one is 1, 5, 3. This one you can understand it as one row with 5 columns of 3-dimensional vectors, and this one 5 rows of 1 column of 3-dimensional vectors, and you want the same combination of these vectors. Now it's a bit more complicated because you have to reshape it in such a way that you are summing the vectors 3 by 3, not a broadcasting operation in the 3, so in the vector. Okay. So if you start with an array like this, that is, we can see it as a list of vectors. No, so every row is going to be a 3-dimensional vector. To make it do this operation, you will need to do this kind of broadcasting. You will need to add the axis, one here and one in the middle. So the last dimension, so the 3, right? So is kept as it is, 3. So the operation happens like in this case. Okay. And so here we create a 1, 10, 3 from our 10, 3. And here we create our 10, 1, 3. And finally, we get the matrix that we want, which is a 10 by 10 by 3. So with the sum element by element in the last row. So now it's 10:25. I will give you 5 to 6 minutes to go over the notebook and try to understand these operations, because we're going to use it later for something. Okay. Okay, let's go. Please, questions on the chat, or if you just please unmute yourself and ask a question here. Okay, please, if there are questions, we can discuss here in the. Please unmute yourself and we can discuss.
So if I get it right, you can only add up two objects that are either identical in all shape dimensions, or if one of the shape dimensions is n, the one in the other array needs to be 1, right? And that is true for all of the dimensions. So 153 and 513 you can add up in the example, but 153, 523 you wouldn't be able to add up.
Yeah, I don't think so. Yeah.
And what it essentially means, wherever there is a 1, you replicate the rest into the matrix, right?
Yeah, exactly. It kind of builds everything goes down to this one, to a scalar plus or and a vector.
So if you have in this example, let's do the same thing now, but with arrays of 3 comma arrays, this A, B, C, D, E. This 153 silently makes out of it a 553 where the A, B, C, D, E appears in every row.
I'm sorry, I didn't understand.
If you want to express this in a mathematical sense as an array or a tensor addition, then what you would silently do is to replace this vector of vectors that you've written A, B, C, D, E into a matrix where in every row you have A, B, C, D, E. And next row again A, B, C, D, E. Next row again A, B, C, D, E. And the number of rows is determined by the number of rows of the second object that you want to add to it.
Okay, yeah.
It probably doesn't do it internally, but this is what you would need to do in order to write it as a proper equation.
Yeah, that that internally I really cannot tell you how it really works, but yeah. Okay, then can we? Okay, I guess we can move to the next one. Okay, so before I was talking about the vectorization, and so the vectorization is the way NumPy is meant to be used, is to do many multiple operations in the use the operation over multiple data of arrays and not one by element. Like for instance, if you want something simple like multiply 2 arrays, you wouldn't loop over them. You just multiply the whole things, and then you get the results in a single line. So it's one line, one operation over multiple data. Okay. Another thing to important in NumPy is to try to use NumPy functions for doing operations with NumPy. So then NumPy has a kind of function that's called ufuncs, which is called which means universal functions, which are functions that operates over the whole array. Like for instance, np exp or sin or sum. No, not sum. They operate over the whole array. So when you apply np exp to an array y, you will get the exponential of all the elements in an array. Okay. Another functions is like dot. Dot is not a universal function, but it's a NumPy function that it can be used for scalar products or generally for matrix multiplication. And this one here, I think is valid also the comment of trying different solutions. It's always I don't know, it can be that there are other ways of doing dot product, but I don't know, this one in particular is the advised one. But when you are writing your code, you should look for different solutions and profile and see what gives you the fastest or lowest memory, depending the requirements in your case. And also something important is that sometimes you have to change your solutions. So how you approach a problem in order to use NumPy functions and do vectorial operations. Sometimes it's not very intuitive how to do it. And one example, this is the last one of NumPy that I want to show because it really illustrates very well how the mindset, how you should approach NumPy is this one of the Euclidean distance matrix. So the distance matrix is so you have two set of vectors. So this one, let's understand it as some data that every vector means something. So you have many rows. Many rows is a vector, and so each row is a different vector. So you have two of these sets, and you want to compute the distance between these two vectors. So you have, for instance, the distance between these two would go here. The distance between these two go here, and so on. We already got something that from the previous notebook with the broadcasting, that we have something very similar, and we got all the combinations of these sums. So from there, we already have a hint that how can we do it, but we're going to explore other solutions. Okay. So okay, you understand now the matrix. This case, you have this, and you want this distance, so the Euclidean distance. And we're going to do the same for the Euclidean distance matrix that looks like this, and the city block distance matrix, also can be known as Manhattan distance matrix, that instead of using the square like here, he uses the absolute value. Instead of being the shortest distance, the distance we normally call, is like going around in a city, you cannot cross through a block, you just have to go around. Okay, so we're going to consider these two problems because they are they pose different approaches that they force you to approach them in a different way. Sorry. Okay, and so the intuitive way, if we don't, let's say, when sometimes many of us we come from C or something, and we try to do a loop over the arrays, and you get something like this. And if we go through the points before, this we are not using, we're not doing it right. We are not using operations over the whole array. Instead of single elements, you were going elements by elements here. So in this case, row by row, we are using a NumPy function, but it's really in this loop, element by element, is really, we're not using it right. And we didn't do any effort for adapting our solutions to the points, to these 2 points. Okay, so this implementation in NumPy with loops, this one you should never do. This is a bad implementation. Okay. Now, to go to the last point, to adapt the solution, we can use something like this. It's a we're going to use a mathematical trick. We're going to rewrite the solution like this. So the distance, so every element is the sum by the row, right? For the rows y and j. And this thing, so this is square, you can write it like this, right? And here I put a vector, it has all the case inside, no? The sum happens with the scalar product. And this scalar product, you can write it itself like this. And the good thing of writing like this is that in NumPy, there are options, functions to compute every of these elements very quickly. So the first one that we already know is dot, that we can do this matrix product here using it. And for that, we pass the whole array with all the columns, and so all the rows at the same time, and we are going to get here immediately all the combinations of the scalar products between x and y for all the ij's. Okay, so this one we know how to do it, and the next two, they are the same. One is y and one is j, but it's the same operation, and we can use this operation that we are going to play with it now. So now don't get scared by it, but this thing means this. So it's what you have here is a sum over j that I should have put k because I used k before, but it's a sum over j over this repeated index, right? And it will give you this. So this is what this one is, and here we have the same for the is what this one gives you. But if you see here, we have y and j's, so that we have to you have to combine them, and you know to combine them, we can use this broadcasting operation, and now we will have them like this, and we're going to sum them, and we're going to have all the y and j combinations, and we already have y and j combinations here. So we sum the whole thing, and we get our result. And now in the notebook, we're going to play with it, and we're going to see that it's very quick. It's a super fast solution. And so we can implement it in a function. So a clear distance matrix, we pass the two arrays. We compute these two parts here, the x times x and the y times y, the xy, and then we sum the whole thing. Okay, and now we can go to the notebook, but it's already 45, so we can make a break now until 11, so 15 minutes break. We are going to play with this, and we're going to compare it with a solution based on the big broadcasting operation, and we're going to see which one is better, and later we're going to profile them. Okay, so let's stop for 15 minutes. And
the last but one slide, why don't you just use a dot product or so for where you use the Einstein summing convention?
Yeah, we're going to discuss that in a notebook after the break.
Okay.
Yeah. Okay, see you in 15 minutes. Okay. Okay, we are back. So we were talking before about the distance matrices, and we're going to start with the Euclidean distance matrix, because the city block is a bit different the way it needs to be implemented. And so we are going now to the notebook 03, Euclidean. And remember here to change also the kernel and put Python HPC 2021. Okay, so here we have two implementations. The first one is based on what we saw in the broadcasting notebook. We have these arrays of vectors, call it a list of vectors, and we get here all the combinations of the difference of the vectors, right? Doing this operation, and now since we have all the differences, we just need to square it, to multiply it, and by itself to get the square of them, and then sum them. So to do the distance, okay? So and then so we have the difference, and then when this part is squaring, and then when we do sum over the last axis, so the axis 2 would be if the shape of our arrays is 5 1 3 after the broadcasting, this 3 here is the axis, is along the vector dimension. Okay, so this one is going to do one implementation of the Euclidean distance matrix, and the other one is the one we already saw on the notebook. And then we're going to see here which one is faster, and we're going to profile them later, and yeah, try to understand what is happening. So here there is a question, advantage and drawbacks of this implementation. And yeah, let's just think about it, and it's going to be more clear when we do the profiling, and we're going to talk about it. Okay, so just keep it in mind, this question, what good or bad things of this one. And okay, so now this explanation here, we can go over it together, but maybe I just gave you some introduction, and I gave you some time, and then we discuss. This is what I explained before in the slides, and it explains just what is einsum. Einsum stands for Einstein summation. In physics in general you see it, but otherwise I don't think it's a common thing. But the idea is this function, what it means is that you're doing the Einstein summation of the multiplication of these two arrays with these indexes. In other words, is you have, I put x, y to differentiate it, but let's say that you have x and y here. You have x, y, k, with ij and ij, and kj. So when you have this operation in Einstein summation, it means that there will be a sum by the axis that, by the index that is repeated. So this one that you're seeing here is, it means that there is a sum over k. So in this case, so what you have is x, yj, and x, yj, sum over j. Okay, and einsum is it gives an extra thing, notation that is not in the part of the Einstein summation, which is arrow I, which is means to it means don't sum, basically. It means to keep it as a vector, no? Because these two are repeated, but it allows you to do not apply the sum rule over a certain axis. Okay, you can understand it like that. And so that's it. So here you can understand what is happening with the formulas. And here there are some playing things. You can play with it and see what the einsum does. And now we consider other alternatives. The dot, that was the question that no, it's not yet. Sorry, this is the dot, the other part of the operation. But here I think, yeah, it's this line here. It explains the question that Dirk was asking, why we don't use dot instead of einsum. And it's because dot doesn't do this operation. Dot we would do if you pass dot x and x, it will tell you that there is a mismatch in the shapes, because it's expecting like mn n k, so this kind of shapes to do a matrix multiplication. And in this case that we have m3, this will be a mismatch, and dot doesn't do it. Okay. So you can play a bit, and here you have other alternatives using x times x sum instead of einsum, and see what happens. And here you time both implementations, and here you check that they give the same answer, the same result. And finally, this is an extra, is to create to consider another implementation, but this one I think we can leave it as a homework if you want to do it. To see the answer, you just run this and you will get the answer here. Okay, so I will give you, it's 11:07. I will give you until 10 minutes, around 10 minutes, because this one is a bit more complicated. And so you go through the notebooks, but remember the notebook is not really about any of the functions that we're seeing here. It's not about einsum. It's just about the main point that you have to take with you is about different solutions. Okay, so this solution with respect to this one, and einsum with respect to what is it, to this one here. Okay, so it's trying different alternatives. So don't get to, if einsum is a bit hard to understand, don't get obsessed about it. Just understand what it does, which is just this operation, and go on. Okay, it's more about different options. Okay, see you in around 10 minutes. Of course, if you want to ask questions, I'm going to be here. Okay, let's go together through the notebook and discuss. Okay, besides the implementation of the functions, the first thing is here is to quick look to einsum. So einsum give you the it would be the scalar vector of every of these vectors in the row by itself. So in this case, this is 10 by 3. When you apply it, you would get a 10 vector. And the second step is to do the broadcasting. It gives you 10, 1. And when you sum this one and this one transpose, this transpose, it will be the same of you would do this one, right? It will give you a 10. It will give you 10 by 10. Okay. So for the other the other term, the 2xy, we get a dot, as before. It gives you all the combinations of scalar products. So this one is every row with itself, and this one will be every row with each other. Okay. And okay, so we use einsum, but we could have used this one that is easier to understand, and it's very simple to write. So it's square this, right, and then sum over this axis. It will give you the scalar products of every row. This one we did already. But here, when we run it, we see that einsum is, at least for these sizes of arrays, is a bit less than, a bit over half faster than, twice faster than this x dot sum axis one. Okay, that's why we selected this. And this again shows again that you should try different solutions to make your code better. Okay. This is another option of NumPy. It's a bit strange to read, but the idea is reduce. It will use a reduce operation. Reduce is from an array to get a bigger, smaller array. And in this case, we give the square array, and this means sum over the axis one using the add function. So you can do, like, I don't know if there is this kind of multiply, and in this case it will multiply along this axis. No, that's what it means. Yes, it's using the sum operation, reducing the array, but it gives you something very similar to this in terms of time. So it's not worth it. So far, we find that einsum is the fastest. And here, finally, we look at the two full implementations, how much time it takes. And here we see that Euclidean broadcast is much slower. It's almost 2 seconds, and Euclidean trick is a tenth of a second. Okay, and we check that they give the same result. No? So 10 to the minus 12 is the difference, is the same result. And this homework that I was talking about, the idea is in the Euclidean broadcast, instead of using this operation here at the end that we saw that is slower than InSum. If you just try to rewrite it with InSum, we can do it better. But it's a bit harder index-wise to understand. So I will leave it optional for you. The answer is not particularly faster because the slow part is the slowest part. No, not the slowest part. Sorry, because this part is already quite slow. And anybody would like to comment, unmute and comment why, what? So it's this part here. No? Why? What can be wrong with this operation?
It's generating an additional stride in memory.
Sorry?
It's generating an additional stride in memory.
Yeah, it's generated exactly. It's generating new memory, right? And actually, it's a large amount of memory because this will be a three-dimensional matrix. It's a lot of data. Okay, thanks. That's it. That's one. Something else? Well, I can say the other one. This one you will have to go to top here and check how much CPU the function is using. Maybe we can do it here. So if we come. We can do something like this. Top. So we can here see how much CPU is using, and oh, I lost it. Sorry, it's here. So we have 99%. Okay, so it went to 100%. And now if we try the other one, the Euclidean trick, we see 500%, right? Almost 600%, 2000. So here we see that this one, Euclidean trick, is multi-threaded, and Euclidean broadcast is not. So there are two things in this implementation. One, that this is a large operation in terms of memory, because it will create this big array, right? And none of these operations here are multi-threaded. They run sequentially. On the other hand, Euclidean trick, you see that it is multi-threaded, and I can tell you this part is not, but nevertheless it's very well implemented. This function is very fast, but this one is the multi-threaded part. So, and there is not a big allocation in memory, as you can see here, or you can expect here, and it uses the whole CPU. It consumes also almost the whole CPU with the multi-threaded implementation. And that's it.
What's multi-threaded? What's not?
Sorry?
How do you know beforehand if something is multi-threaded or not?
No, you don't know it. You have to. I mean, maybe in the documentation you can find it, but in general, you have to profile and you have to look at top, just to look how your function is working.
And how do I get the terminal? I mean, you had it there
This
on
terminal. you come here to this folder. Oh, I'm sorry. You can go here, file, new terminal. Okay. And then you can move it if you want to.
That's the terminal of the node where you're logged in, huh?
Yes, yes, exactly.
Because I noted if I'm going on a regular terminal outside the web browser, I cannot log in onto that node.
No. Yeah, this one you get the terminal where Jupyter is running. Okay.
Mm-hmm.
Okay. So now we can. We can go to the profile to the profiling part. This is it for this notebook. If somebody has a question, please let me check the chat. Is there a list of function functionality? Yeah, the question of Sebastian is similar to what Dirk was asking. Yeah, there are some of the functions in NumPy use multiple threads. In particular, very known is the dot, but at least I don't know by heart. I know dot, for instance, that it does, and I know that some doesn't, or this something doesn't. So you have to go and try them and yeah, look how your code is running. Yeah. And there is a question. So Adrien asked a question before about about this multi-threading of dot. He's asking if dot use OpenMP threads. What about if it is used in a context where there are many ranks running? So this one is what we're going to see on Friday. So if you have this Euclidean trick running in somehow you manage to make it use multiple ranks in your code using NPI for Pi or using Dask. This is what we're going to see in particular in this course. And you have many ranks, so many processes running the same function. Now dot cannot use all the threads because the threads and the ranks are going to, they will have to share the CPU, and there is only a finite amount of threads and processes that can run in a CPU. And then, for instance, if you run it in two ranks, so you have two processes running a Euclidean trick, now np-dot cannot go and use the 12, well, in this case there are 24 with virtual and physical. No? We have 2 threads per core. So it cannot use the 24 cores. Instead, it can use 12 and 12. And if you have like 24 ranks running, then dot is not going to be parallel at all. It's going to run sequentially in the core that it managed to get. So it won't try to run in parallel and create a mess with the ranks. If this is the concept of your question, so it will just take less whatever is available for threads. Okay. And now, what is the best solution if many ranks? If you manage to split the data, or less ranks and more OMP threads, that one you have to check yourself. You have to go and see one rank, 24 threads, 2 ranks, 12 threads, and so on, and check which one is the fastest setup. Okay. Okay, now so we're going to continue with these 2 functions, and we are going out here to we go up and we go to profiling. So this folder, profiling, so Python HPC profiling, and let's open a line profiler, the first one, 01 line profiler. So here in line profiler, again, please change to Python HPC 2021. Here in line profiler notebook, we have the two functions again, Euclidean trig and Euclidean broadcast. And we're going to see different ways of profiling. So the first one is what we already know, time meet. Time meet, somebody already asked earlier, it will take whatever you pass it, and it will run it many times, and it will get some averages. It will get the average time and the error, and by default it will run as many times as it needs to get a small error. Okay, but we'll comment this one in a second. You can use by hand these commands, and now it does one run and one loop. And how it works is I don't know exactly what's the logic behind to tell you the truth, but it has two loops. One that is controlled by n, so it will run many times Euclidean, and above that it will have another loop that will get average from the inner loops. And here you can control that by this number here. So in this case, it will be one inner loop and one outer loop. So one run and one loop, and you see there is some value. And here it will run twice. And I guess if you put more loops here is when it will give you some error. Yeah, it will try to compute some error. So with these two numbers, you can control how many times you're going to run. Okay. Okay, this is time it. It comes with it's already on the notebook. You don't have to install it or anything. The next one is line profiler. So line profiler, you have to install it, pip install, and you have to load the extension in the notebook. And this will make available this magic command, lp run, line profiler run. Here you can see with this question mark, you can see the options. It has some couple of options you can change, but the idea how to run it in short is you pass a statement, some code that you want to run. In this case, is this call Euclidean trig in x, and you pass what do you want to measure within this code. So imagine that this is something longer that calls Euclidean trig. You can pass here the function that you want to refine. Okay, in this case, it's the same. It's the function. So this is just redundant, but okay. So when you run it, you get this. It's a very nice table. You see total time is the first thing that it gives you. That we already got it from time meet, and it has the time by lines. So hit is the first column, is the number of times that that the line appears. So in this case, it's only one. But if this is inside of a for loop, if you have for I in range something, and you're running this one many times, you could get here like hit 5 times, 10 times, yeah, because it's the number of times that this line was executed. Okay. So it gives you the time by line. So you have here, it's here the unit is it's microseconds, right? Microseconds, and it's very nice. You have it by time, and like this is you can find what are the slow lines in your code. Okay, here what is making the thing taking most of the time is not the dot, is the final sum. Okay, for instance. But it can really help you to understand which parts of the code you may need to look at or to change without having to go one by one and checking. In the other hand, I wouldn't recommend to do this for very long. I don't know, for a super long script. I think it's better to, in my opinion, no? To kind of have all your functionalities in functions and profile them apart. I think can make the process easier. Okay. Okay, this one was Euclidean trick. Now Euclidean broadcast is the same. Sorry, here it gives the percentage. I stopped talking about the columns. Here's the hits, here is the total time per hit, and here the percentage. And here we see that both of them, they account around 50%. So both operations are a bit slow compared to how it happens here. And yeah, we already know why. No, this one is not multi-threaded, and this one may create a lot of memory that we're going to profile after we finish with this one. Okay, and that's it. This is line profiler, and the last one I want to show you is C profile. It also, I think it comes it's directly in the notebook. You don't have to store anything. It comes with Python, if I am not mistaken. And this one is a bit more like for developer kind of application, because it really goes to the internals and things that I don't know, you may not be interested in your, I don't know, in your day-to-day work, unless you're doing very, I don't know, changing the internals or doing very sophisticated or very fine-grained profile. Okay, but anyway, it is there. And okay, there you have some options to profile. Other things that we can do to profile is to check the memory, and there is something very similar to this one. That is called main profiler. And now main profiler doesn't work in the notebook, but you have to do it on a shell. But it's very simple anyway. You load it from main profiler, import profile. This is something also that you have to install. It doesn't come with Python directly. And you just take the function that you want to profile and you decorate it with profile that you imported here, and you run it. And then when you run it, it will give you a table similar to the one we got. So to run it, we can open a terminal, new terminal, and we can go to our Scratch where we have the HPC Python. The Python HPC. So we go to profiler, and we can do this thing. I will paste it on the general channel, that we need to activate environment. Otherwise, you won't have the right Python. So I will copy and paste this. Control-C. Please copy and run this if you want to run the main profiler. Use a source. And now you will have the so the Python is the right Python. So let's run it. So 02 main profiler. You run it like anything in Python, and you get a table very similar to the other one. So you start with the memory until the point that the function is run. Okay, so this one is the base memory, so you don't care. You have to look. Mostly, you're more worried, interested on increment. So how much every line increments. Okay. So here we have these two lines. The increment is apparently virtually nothing, 0 megabytes. Maybe something smaller than megabytes, but. And then you have dot, which it increases in 31 megabytes, and in total, the last one it increased another 30. So you got like 50, around 60 megabytes in total is the memory footprint of your function. And just remember this 100 megabytes, because now we are going to do the same for line profiler, and we're going to see how much is it. So now line profiler, so it starts with the base is the same, because the program is the same. And this first thing that we knew already, that it may use some memory, because it's slow and because it creates a three-dimensional array of flow 64, which is the default of this arrays that we have here. It uses 1.5 gigabytes of, so it's 1500 megabytes. So here you have to allocate a lot of memory. Okay, and finally this one is not more than this. It's pretty much similar to what we consume here. So in this case, if you have to decide between these two options, between the line profiler and the time meet, so you know that this one is faster, and sorry, this one Euclidean trick is faster, and this one you see that besides being slow, not all besides, I guess the being slow is part of the, because of this. It creates a lot of memory, so it does a large memory operation that you can avoid with this implementation. And here in total we saw three things. We saw we're seeing now the memory that is relevant to decide which implementation we can go for. We saw the time that it takes, and we saw also with top, we saw if something is using multiple threads or not. So with these three things, although the time can be alone, it's already a good indicator. But sometimes memory is relevant if you have more data. If you have less amount of data, it will be for sure relevant. But with these three things, top, time meter or line profiler, and memory profiler, you can really have a good idea of which implementation you should go for. Okay, and here there are also, I included here a line profiler in the notebook. Oh, sorry, outside of the notebook. And is the 05. You run it similar to main profiler, and it the way it works is so you load the line profiler. They don't have the decorator, but you can sort of do it by hand. So you create the line profiler object, and you run your function wrapped, you see. kind of decorated by the line profiler, and then you say line profiler print stats, and it will give you this table that we already knew from the notebook. And yeah, by the way, this kernel, we're going to keep it for after the course finishes. So if you want to use it, use this kind of stuff and all the things we have installed, and you will see them during the training, I recommend you to copy so to make the kernel in your PCDynit account using the same the script that we run. If you want, you can save the script in your account. Just copy it from the place it is in the general channel, and you can keep using it if you want. I don't know how long we're going to have it, so don't rely on it for production, but you can keep using it. Okay. And I think that, let me see the chat. Oh, there was a problem here. Okay, it's solved. Okay, for usage in the future. Okay, thank you, Adrian. Yeah, this is the two scripts. No, I'm sorry. I thought I understood wrong. Yes, but there is also a module load that you may also need. So you can copy the scripts, the two scripts. Okay. And yeah, if there are questions, otherwise, that's it for the morning. I just wanted to show you one other slide that okay. Oh. So I can show you this slide that the trick that we use. So this thing now for the city block distance matrix we cannot use, because with the apps you cannot apply this mathematical trick. So we will have to look for other alternatives, and through the course you will see we are going to see different versions of how to make this one that they cannot be done as fast as the other one with only NumPy. Okay, and to finalize, just to take with you, just remember the main points of NumPy, which is do everything that you can do it vectorially. So with using vectorial operations, use NumPy functions for it, and try different solutions. Don't stick with the first solution that you see, or try different solutions and profile, and in many cases you can really speed up your work. Okay, it's then 11:54. I think we can stop now if there are no questions, and see you guys at 1. Well, actually, no, with me, with Theo for Cython, and in the afternoon we are going to have F2Py and CFFI to write C and Fortran native bindings. Okay, have a nice break and enjoy your lunch.
Okay, so I guess I can start. So today in the afternoon, we are going to start talking a little bit about Cython. So I'm going to refer to the basic things from inside the Jupyter notebook, where you can interactively compile Cython code. I will talk about what Cython is, where you can use it, and what are the disadvantages. And tomorrow we will see some more complicated stuff that you can do with Cython, like integrating external C libraries, how you can compile outside of the Jupyter notebook and use templates and C++ classes and from within your Python/Cython code. So let's start. I'm in my Python HPC directory, which you have downloaded, and I will go inside the Cython directory, and in the notebooks, I will open Cython 1. Okay, so is the size fine? I guess it's fine. Okay, so let's start. So the header here says optimizing Python code with Cython. I have loaded my Python HPC 2021 kernel. So make sure that you have this loaded as well, because it has the Cython version that we are going to use. And so we are all the same page. So in the first cell here, I don't do anything critical. I just import Cython here, and I import some stuff that we're going to use later, like NumPy, the math from Python, random from Python, the standard Python library, and just matplotlib, so that we can have some fun with plotting and see our results. And in order to be able to use the Cython extension from within Jupyter, we have to do this load ext Cython. So I run this, and now I'm ready to go. Let me just clear the kernel so that we do that again. And you see, I import everything I need, and this is the crucial part for today, the load ext Cython, which basically tells Jupyter, instructs Jupyter to do some magic for Cython, so that we can compile the Cython code from within a Jupyter notebook. So I have here a simple Python function, which more or less calculates pi using the Monte Carlo method. So to give you a perspective of how this is done, it's like throwing darts randomly inside a rectangle, and for each dart we check whether this dart lies inside a circle with radius 1, and then we count all the random darts that we have thrown, and we see which of the darts are inside the circle, and from within that we can estimate the number pi. So more or less we have a fraction here where we do the number of the darts that are inside the circle and the ones that we have thrown totally. So this is my function. I call it pi MC for pi Monte Carlo, and this is the default. I throw 1,000 darts, 1,000 random points. So let us run with, it's here about, so 10, this is 10 million points, and I time it. So you see that it this is the actual estimation of pi. It's quite good. And this is different than time it because it just runs my calculation once and it reports the time it took for the calculation to execute. Okay, so let's now go to Cython. Here, as I said, using the low-text Cython, we are now allowed to use this Cython magic, which goes on the top of the cell that we want to instruct Jupyter to compile using Cython. And here I just copied the same function as above. I didn't do any change. So this did the compilation. Let me run for the same number. So this underscore here is just so that you can better see the thousands here. It doesn't do anything. So I time my Python, and you see that just compiling the Cython, the Python function with Cython without doing any change, I get a speed up about 30%. I guess it's 1.67 seconds, and here it's 2.37. So this is really fine. And what I want to stress here is that every Python code that you have, apart from some very few exceptions that I won't talk about, but you can see it of Python, the Cython documentation, every Python code is also a valid Cython code. So did we do all that just to get a 30% speed up for our Python code? And the answer is no. So here is where we start going into Cython in more detail and show how we can take advantage of it to optimize and accelerate our code. So Rafael mentioned in the morning some things about Python and the GIL, threading and everything. So Python is really slow, especially if you have a loop-based code. So because of its nature, because of it's an interpreted language, and because of its dynamic nature, it makes a lot of checks when running to make sure that everything works correctly. And on the other side, if you go to C, I don't know how many of you are familiar with C. C is much stricter in this sense, so that you have to specify and declare and define your variables, what type your variable is. And so that's one of the reasons why it's much faster. So we can start doing a little bit of hybrid between Python and C code, and we start introducing some type declarations that Cython has to start stepping out of the dynamic nature of Python and to let Cython produce efficient C code for us. So the only difference that you see here is that now, instead of having just in circle equals 0, I say that cdef int in circle equals 0. So cdef is a keyword of Cython, which is more or less instructs Cython to generate efficient code, since it now knows that this is an actual integer value, an integer in C terms. And I do the same for I, which is here the for loop index. And then I use cdef double for x, y, which are the coordinates of my random point. So now this for loop uses I as the index, which is an integer. So for every iteration of the for loop, now we don't have to do all the Python checks for the type of I. So let me compile this. And now I have PyMC. I should have called it differently, but in any case, let me run it. So you see that we went from 2.37 seconds to 0.4 seconds. So 403 milliseconds are 0.4 seconds. So you see here that just by giving Cython the information to produce efficient code for these three variables, we are much better than before. So any questions up to now?
Yes, you mentioned several times compiled code. Is this really compiled?
Yeah, I will show you now how it looks when it compiles.
And the second question that I also have is, what apparently makes a big difference is that you do pre-declare variable types.
Yeah.
So there is not this assumptions to be made by Python because the function that you're using spits out a double. So also the variable that you assign it to must be double. And
Yes.
then would this run into a regular Python style error message if you mix up types?
Okay, so to answer to your question, I will go inside this function where I use some more Cython magic to show you actually what the C code that it produces looks like and how it interacts with Python.
Okay.
Okay, so here I do the same as before. And just to show that I show you also another way of using cdef. We don't have to use the cdef keyword all the time. We just use cdef here with colon, and underneath we declare our and we define our variables here. So it's like putting cdef in each one of them, but it's clear here. So it's clear also to see that here are all my type declarations, and it's better. So we use the Cython Jupyter magic here, and now I pass an option which is called annotate. So if I run now this, Cython will give me some information regarding the interaction that happens with Cython. So the yellow lines here indicate a Python interaction. So if I go here, you see all the Cython code that is generated from this is actually the C code that Cython generates to make to glue this thing with Python. And here it does everything for us. It's a little bit complicated to find out what is happening. But you see here that I just have a plus, and here, because I did with cdef, I defined my variables, we have no Python interaction. So the more yellow this is, it signifies more Python interaction, which is an indicator that tells us that this is going to be slower. So you see here that I have x, y, and because I use the random from Python, it shows a Python interaction, although I have already declared x and y to be doubles. And here again, I have a Python interaction. So let me time it, and we see again it's 402 ms. So let me go again to this one here that we had initially with Cython without the variable declarations. And if I do like that, you see now that all this stuff are yellow. Even this is yellow, not a very bright one, but the for loop, the if, the int circle, everything is yellow, which is why our code is very slow in this case. So here I executed the above. Let me compile again. You see 1.66 was the one without declarations, and now 4.11 is the one including the declarations. So is this clear up to now? So more or less, by moving from Python gradually towards C, we start gaining the advantages of C. So you see here that we just let Cython know that the type of our variables, and it optimizes the code. So let me talk now about Cython functions. Yeah.
May I just ask, or put it in my words to see if I got it right? Whatever pops out in yellow is taken directly from the Python interpreter functionality, whereas what remains in white is translated to C and kind of just in time compiled, or?
No, this is compiled ahead of time, the time that I press the button here. So this would normally, outside of Jupyter, would include a separate step that you compile, and then you can use the Cython code. So,
but whatever remains white is really compiled into standard C, or translated into standard C and then ahead of time compiled.
No, it is translated in standard C, and then it compiles the C code that is generated, more or less.
All right. Thank you.
So, as I mentioned, we are moving gradually towards more C-like code by using these type declarations, and therefore we can gain a large speed up of our code, and we will see later how this translates also in parallel execution. So now you see here that I have defined my function, the pymc. I used the standard def from Python. So actually, Cython provides 3 types of functions. So we have the typical def functions that can be called from Python and Cython code. I will show you what the difference is. Then we have functions that are declared with cdef, and with cdef in front instead of def, we are saying that this function can only be called from another Cython function. So you cannot call this function from Cython code. So this can be used, for example, when we have an expensive calculation that is used as a part of a larger function that we will expose to Python in the end. But the calculation per se does not need to be visible outside Cython. And then we have the hybrid, the cpdef, which basically tells Cython to generate 2 different versions of the functions. So it's like having both cdef and the normal def function. So whenever we use the produce function from inside Cython code, Cython is clever enough to use the optimized cdef version of the function, while we can use the same function from the Python code, but then it will use the def version of this function. So this gives us both versions, and Cython is clever enough to know which one to use. So if I compile now, let me add here, so I can do a cube sum of 1.2, which of course will return 9. But if I do cube1, which is this function here, it will tell me that cube is not defined. While you see here that since this was a Cython function, I could access the CDEF from within it. So the advantage here is that I don't have to run my function twice. I use the cpdef, and I can call it both from Cython and from Python. So again, the cube sum can be called from Python as if it was a normal Python function, while it's Cython 1. Also, since we are using this kind of function that is more or less one line of code, and suppose that we were using this function a lot of times inside a for loop from within a Cython code, we could instruct Cython to use inline, which basically will avoid the overhead of calling the function every time. So whenever it sees the function call, it will replace with the actual body here. So instead of having the actual overhead of calling cube every time, it will replace this cube with x to the third power, etc. So I put the annotate also here, and you see that since this a cdef, there's no interaction. And you see here that it added the inline. Here, because it is a cpdef, so there is an interaction with Python in the interface. Since we are able to call this function from Python, you see that it has yellow here. While here, because we said that the return type is a double, and basically here is pure Cython code, there is no Python interaction. So is this clear? Any question? I cannot see the chat, so if you have any question, please unmute your microphone and let me know. So again, we saw the three types of Cython functions, which are the cdef, called from Cython only, the def, which is the normal def Python code, which basically means that we can call our function from Python, and then we have the hybrid of the two, which is the cpdef, which tells Cython generate two versions of the function, and whenever you have interaction from within C, use the optimized one, and whenever you have interaction with Python, use the def version of it. And we saw also the inline to optimize more our code. Now, the basic package, the most important package for numeric computation, where many other packages are based on in Python, is NumPy. So with Cython, you already have support for NumPy arrays, and Cython allows you to access the contents of the NumPy arrays by the so-called memory views. So here is a function that sums more or less the members of this vector that I pass here. And here is how I tell Cython that I am expecting a vector, a NumPy vector. So you see here, this is a vector because it has only one column. If I had a matrix, it would be like that. So with this notation, I say more or less to Cython that you should expect a vector. So I do this here, and here you see there is a slight interaction because of the memory view, but here there is no interaction. And I have my sum, and this is it. So we can go away with the Python interaction a little bit. So you see here now we don't have the Python interaction here because I also told Cython that double is my return type. Now let's try this. Of course, you can do that in NumPy much more easily, but this is just to demonstrate how you can start using Cython with NumPy arrays. So here I generate X, which is a vector filled with ones, and its type float 64 since we declare this to accept a vector of doubles. And here with S1, I compute my sum with my function above, and here I use NumPy. And you see that, as expected, the summation works in both ways fine. Here also we have my sum to D, which is more or less the same, but I wanted to show you how we can start interacting with arrays that have 2 dimensions. So here you have a matrix more or less, and Cython knows what to expect. So here you see that I will test this with ones again, but now I give it a 1000 by 1000 shape. So this is a 2D array, and I can calculate, of course, with NumPy's version of sum and my sum that I have created above. Any question? Okay. So now let's move on to another optimization that you can do with Cython. So I mentioned here that you can work with NumPy arrays by using the so-called Cython memory views. So basically, this is a view of the NumPy array that you're passing to Cython, to a Cython function, and then Cython can access using indexing the data of the underlying NumPy array. So I used here the s plus equal xi, but here you see there's a small Python interaction. So the reason for that is that although I tell Cython that this is a memory view of the underlying NumPy array, Cython, to be on the safe side, will check in every iteration of the loop that I'm not exceeding the length of the NumPy of the underlying NumPy array. So here it will not allow me to access X. I had 1000, it will not allow me to access X 2000, for example. And this is for safety, but since we already took the X shape here, and we know that the loop won't run beyond the shape, the length of the array, we are sure that this is safe. So we can tell Cython that we don't want to check, to do all this checking for us. So there is this decorator, which you can see here from Cython, C import. I will explain what wraparound is. And you see the bounds check. So by decorating my function with bound check false, I tell now Cython to stop doing this check every time I try accessing an array with some specific index. So here I have the 2D version, and since I know the rows and the columns of I took from the shape of the array, I know exactly what I'm doing, and I'm not going to ask for elements outside the extent of the array. So you see here that now that we are not doing a bounce check, we no longer have this interaction with Python. You see here, we have a slight interaction because the checking is done to make sure that we don't ask for an element outside the array. The other thing that we can do is that since we are not using negative indices here, so you know from Python in general that, and from NumPy, that I can have an array like that, and if I print x, this is the array 0 to 9. So I can ask for a negative index, which means -1 starting from the end. So this is the last element of the array. So this is 9, which is the same as x8. So for more optimization, I can tell Cython to stop doing also the negative indexing wraparound, as it's called. And because I don't use negative indexes here, I go from 0 to the number of rows and from 0 to the number of columns. And this produces even more optimized code. So let me take this, and it here. Oh, yeah. So you see that because I have allocated a one-dimensional array, it tells me that the buffer has wrong number of dimensions. So I need a two-dimensional array here. So again, we have the correct value. We can time it also. So I can say, for example, my sum slow here. And I can time how much time it takes for the slow one. Let's see. So it will do some iterations. So that's why it takes some time. So you see that it was a little bit faster, the one where we disabled all the checks that Cython does for its loop. And so any questions?
Yeah, there is
So
a question on, sorry.
Yeah.
So I just tried to time the Python version as well, and it seems to be faster. Do you have any explanation for that?
The Python version, you mean this?
Yes.
Yeah, so this is not exactly the Python version, it's the NumPy version. So for that simple calculation, probably NumPy is already much more optimized than the double for loop that we did here. So this was just for demonstration, so that's why I added this here, because NumPy will for sure be faster than this, because it's already, it has an optimized version for accessing the array elements, and probably it could be even parallelized.
Okay, thanks.
So yeah, so I will mention in the end what are the disadvantages of Cython.
Theo, there is a question also in the Slack channel.
Yeah.
Is there also such an easy way to use Cython in regular Python code, or without using the Jupyter notebook, the magic?
Yeah, so here I decided to start using the Cython magic so that I don't focus your attention on how to compile the Cython code, because this is something different, it needs some attention. So I wanted to show you how how Cython looks like as a language, and I have some examples of how you can do this from the outside. If we have time today, I will show you, otherwise tomorrow. But I will show you how to compile both a Cython code and also have a Cython code which interfaces with a code library that you have already in C. So this is the easier way, because otherwise we have to do some things ourselves manually. And for demonstration, it's much easier to use the Cython magic.
Theo, may I ask one question about these timings that I forgot to ask earlier with Raphael? Are these really word clock times or CPU times? And can it show you in any way how many cores are being used? Does it include that information?
So you can define how many calls you mean. Here it says that it ran, for example, 7 runs with 1,000 loop seats. So it's a total of 7,000 times. So you can pass some things here.
That was clear. But the time that was given here as an average for the 7,000 runs, is that a word clock time?
So it's the CPU time. So here,
let's say this is a single core run, and it would be able to do it on 8 cores.
Yeah.
Would you 1/8 of the time? If it was parallelizing?
It depends on the implementation that you do. I will show you how to parallelize with Cython, and you see compared to the single core how it differs.
So you would then see a smaller number, because
yeah.
That means it's a word clock time, I guess, huh?
Yeah, it's the not the CPU, sorry, it's the word clock time, yeah.
But it doesn't give you it cannot give you the information on this line how many cores were active, how many threads.
No, for that you need something else to see what it's.
Thank you.
Okay, so if there is any other question, otherwise I can go on. So here I have an example of more compute intensive calculation than the summation we have here, and something that you cannot really do with just NumPy.sum. So here I calculate the Julia set. I don't know how many of you are familiar with the Julia set. So more or less what I'm doing is that I'm using a grid in the complex domain, in the complex space where X is the real axis and Y is the imaginary axis. And I give some number and I make some iteration based on the formula. And based on the number of iterations that are needed for the absolute value of the norm of the modulus of the complex number to explode, I give a particular color to the pixel that corresponds to this complex value. So it's better to see it in how it looks like. And here I have more or less used the mesh grid to create 2D arrays for X and Y, which I will pass here to the Julia set. And you see here something else, that since I know that these values are not going to change, I can pass the Cython const, which is like the C const, which is also an extra check for the compiler to make sure that I don't change the values of the array here. Then I pass the real part of the actual number that I want to use. This is the imaginary part of the number. This is the maximum number of iterations. Here is a radius that determines what I mean by the complex modulus exploding. So when it's outside of this radius, I consider it that it has exceeded the value that I want, and it belongs to it belongs to the Julia set. And here is the actual return, the matrix that I'm going to return. So I have here Julia set Cython, create the mesh grid. C here is the complex number, which I take the real and imaginary part, and I plot the Julia set. So you see here that this part more or less does not explode. That's why it's green. And as I move, it's yellow. And as I move outside, because the values of the imaginary and the real axis are larger, it starts exploding more or less after some iterations. And based on the number of iterations, you see a different color. So you can get different pictures by using some other value of C, for example, because even if you have a slightly different value of C here, you will see a completely different picture. So you see, now here, for example, I can have something else here. You can play with it and see how it looks like for you. So just to be fair with the other comparison, because this number here affects the number of iterations for each element. So let me run again and make sure that we time it right. I put 100 iterations here. So it's 745 milliseconds for this particular number. So again, I have my CDF here for everything. I have my two double loops here. And the reason that I have included this calculation is that it has some computation happening, because for each pixel, I have to do this while loop. And also because each pixel is independent of the others. So this can be easily parallelized. So we can parallelize and say that we want each processor to get a different row of the actual image. So processor 1 will take some number of rows here. Processor 2 will take some other number of rows. And so this, because they are independent, we can gain a speed up because of the CPUs have enough work to do. So to do that, we have to import from Cython.parallel p-range, which is a parallel range. And here I change my range to p range. And to make it work correctly, to be able to parallelize, I have to pass also the no-GIL equals true. So during the morning session, Raphael showed you that Python has the global interpreter lock. So that means that from Python, it only one thread, from one Python interpreter, only one thread can be used at a time. So if you have multiple cores without releasing this global interpreter lock, we cannot use many threads at the same time, because we can use many threads, but they will not run in parallel. So let me run this. I compile with p-range, everything is fine. So this 745 milliseconds. So this is the same calculation. Let's run again. So 746 milliseconds. Let me run this just to make sure that. Put a parallel here to make sure that we are using the same and nothing wrong is happening. Compile again. So no speed up. So does anybody know why this might be happening? I used p-range here. My computations are independent and nothing is happening.
Can you explicitly control the number of threads to be used?
You can do it, but by default, it will use the threads that OpenMP tells it to. So here I used p-range, it should work, right? So here is one of the things that you have to be careful with Cython. It does not automatically parallelize the things for you if you don't specify the correct compiler flags, your compiler. So I have added it here some more so that we don't directly see the answer. So here I have to tell Cython to pass some extra compile args and extra link args. So this is something that should be just below the Cython magic, and it starts like a Python comment, but it really is not. So I tell Cython when it compiles to use this OpenMP flag, which would be the OpenMP flag that we would use if we were compiling a C code by hand and we wanted to enable OpenMP. So let me.
But sorry, if you do OpenMP, normally you have to put in pragmas.
Yeah, so that's what the p-range does for you.
So how does it know what to do?
That's the magic. So
well, it's not so magical if you have to do it yourself, right?
You have to pass the OpenMP flag because otherwise it does not know what to do. So this is something where Cython needs a little bit more work compared to the things that we will use later, like NumPy.
Yes, but normally.
But I think the pragma can be there anyway, so they will be just ignored if you don't use this flag.
Yeah,
So
the pragma will be there, but if you don't say the compiler that I want to interpret this pragma, it will just you pass it as garbage.
I don't see any pragmas. Anything where it says this should be private, this should be global, and here you should do the parallelization. Where are they?
So here I will show you. I compiled with OpenMP, and here I called, of course, the wrong version. Let me OMP. So I call it here. Let's see if we gain any speed up. So we dropped from 750 to 155. So let me annotate this so that we can see what it produces for us. Okay. Okay. You see? It has generated.
I believe you, but how does it know how you want to generate it? I mean, you can do the parallelization in any loop that you want. One is better than the other. And
Yeah.
sometimes you have to pay attention to see what's a local variable and not.
Yeah, I know. That's one of the problems of that you don't really have much control on that. And for a simple thing like this here, it's easy to understand because it's completely independent. But for more complicated stuff, it's more complicated as well.
So if you had like a loop running over not 10 lines, but 500 lines, which happens in real code, there would be no way that this could give you any OpenMP speed up, right?
Well, it really depends on how much you want to do in terms of getting the help that Cython provides for you. Otherwise, if you want more control, you can go outside, you can write this completely in C and then call it from Cython.
I see, okay.
The help that you get is as far as you don't want to mess with C. So if you know exactly what you want to do in the optimizations, and you really want to optimize something, or you want to use something that is already optimized and uses OpenMP, then you can generate manually better code.
Okay, thanks.
I also have a question.
Yeah.
Yeah, usually when you pass parameter to a function in Python, you cannot modify them inside the function. You have to use return. And here it seems that you can modify Julia, the matrix, from inside the function.
Mm-hmm.
And isn't it super confusing when you mix it with some Python code?
So yes, here I used this notation here because I wanted to pre-allocate more or less the Julia array. But you can do that with Cython as well and return it. So this is true for memory views, you see here. Because this is a memory view that is not constant, I can more or less mess with its contents. So even if you have a normal NumPy array, you can change its contents. You can mess with the contents without changing the identity of the matrix. You understand what I mean? So
Yeah.
a NumPy array is not really immutable.
Okay.
So
but the memory view is mutable then.
The memory view, if you don't specify as const, it's mutable. If I specify this here, you see const.
Yeah, it will not be the case anymore.
You see?
Yeah. But the point is that usually you never do that in Python. So isn't it quite confusing when you call a function in Python? Usually you know that it will not mess with any of the parameter.
Yeah, so you're right. So initially, before things like NumPy came into place, or CuPy or whatever, if you wanted to interact in a type of Pythonic way with C code, you had to write some hybrid code that really starts going away from what you are used from Python. So Cython, what I think about Cython is that it's very good, but its power is really there when you want to interact with C code or a C library that somebody else has written, and you want to somehow be able to interact with it from Python. So if you want to use NumPy arrays and you already have some library that you know works with, like arrays in C terms, arrays like pointers and whatever, and you know that this library is working well, you can go and use Cython. This is the best situation that you have. So if you look at codes like MPI for Py, H5Py, NetCDF for Python, all these libraries that have like the library name and for Python probably are using Cython to make this interface between Python and Cython. So there are better ways and more portable ways for you, like NumPy, for example, to give you a better result and better performance if you just want to optimize a single Python function.
Okay, thanks.
So I will show later how you can work with a code or a C library that you have created and you want to interact with it like it was a Python function. But again, you have Cython has a lot of stuff, and it's good to have an understanding of what is happening underneath and have a clear understanding of what all the CDEF things are and how the whole interaction works. So any other question? Otherwise, I can proceed. So we'll see in a calculation like that with NumPy, it's much easier to do. Okay. So I'm stopping this. And actually we could see, probably we could see the CPU utilization using this here. So this is a plugin from NVIDIA that we could see that it's actually using all the CPUs. Like if I run here, you will see the CPU. Yeah, so this was the erroneous one. And let me see. So here the calculation is not that big, so it cannot really catch it, but I can give it something bigger. so that we actually see that it's so the calculations are very fast and doesn't have time to cast. I can put more iterations. Like so you see that again, it's not optimal, but it uses more than one core. Close this and go to Cython 2. Okay. So here I will start showing you some more stuff that Cython provides, some additional Cython features. And first of all, I will show you the automatic type inference. So here we have again the Cython. This is a shorthand for annotate. And I tell Cython to infer the types of my function, so I don't have to use the cdef again. So I pass this with infer types equals to true. So here you see that it inferred this. It could infer x and y because I passed my rand here. I wrapped the random function from random to an inline double. So from here it shows that it understands from the definition, from the initialization, that my rand will return a double, and it will infer that x is actually a double. So in circle, it realized that it is an integer. And here for I don't think that it realized that it is an integer. So I can go and tell it like that. And again, here I can give it a little bit more help, but since the range is coming from Python, cannot really find, and there's an interaction here. So instead of going with cdef and defining everything, you can let Cython help you if you're not really familiar with C, and get some speed up from not including the types yourself by using the infer types equals true. So if I use the infer here, you see that again I have a good timing like before, where I had to define my own types. So let's have it without the infer types. We'll see that what I mean. So here have PyMC, and the inferred one took like that, and the normal one is not as fast by a small margin, but again, it's not that fast. Yeah, is that
Wait, may I ask? In the beginning, you were showing the various steps of building up Cython with C constructs, such as including type definition of variables and so on.
yeah.
There also implicitly inferred initially what type a variable was, like in Python, and that was valid in Cython as well. So does this infer construct mean that it infers at compile time rather than at runtime?
Yeah, so if something is not inferred or explicitly declared to be a particular type, then Cython can use it as a Python object because it will use an actual Python object for it. So if it cannot infer that something is an integer, it will use a Python object for it, and which comes with all the overhead that Python has.
Okay, so
that's why everything that I don't explicitly define, it can use, but it falls back to Python.
Okay.
So you can see here, for example, I have the in circle here that I didn't use the infer. Let me have it as def. And you see that some of the things are not really, it adds a lot of code because it cannot be sure what the object is, and it has to make the checks. So it can interact with whatever, but it will use a Python object for it instead of an actual integer.
But then, developing this idea further, could you use any kind of more complex Python code and just put in this $, whatever it was, Cython in the beginning, and the construct to infer variable types, and so every Python code would get faster without doing anything?
Well, I don't know if this is really true, because there are some things that Cython does not allow you to do. You cannot do this for everything, and therefore you lose some of the things that Python provides when you're going to Cython code, and therefore you should not really compile everything in C for that.
I see.
And also, as I said in the beginning, Cython is better when you want to interact with something that is already C.
Yeah.
Now, to be able to use Cython in a more object-oriented way, so that you can interact also with classes, with C++ classes, Cython also allows you to define classes. So here I have a normal Python class. I call it PyRectangle. It's not something really complicated. So I can have square equals PyRectangle 1.1, and I can use square and I can use the method. I suppose that you're all familiar with this. But now you can have Cython classes. So here, instead of the class PyRectangle, I have the class CyRectangle, and instead of init, I have the cinit. Here are my fields. I define them with cdef $x and y, and I have two methods which I define with cpdef. So I can compile, and I can have a CyRectangle, and I can call the area and the perimeter. One difference here is that I can do with a Python class, I can access my square x. Let me do it also here. It tells me that object has no attribute x. Why is that? Can anybody tell me why is that? Any idea?
Because it's CDEF, so it can only be accessed within CPython.
Exactly. It's CDEF, so although I can access it from within Cython functions, you see here x, y, I cannot access it outside. And suppose that this function here was CDEF also, this method. I click this. If I try to access it, like calling it with area, it won't allow me. While the perimeter was CPDEF and it was fine. So the x and y are only visible from inside Cython functions. Outside, I cannot access them, which is completely different from what is happening here. So again, the CPDEF and CDEF rules that I spoke about in terms of normal Cython functions apply here too, but they also apply for the variables here that you have CDEF, and these are more or less your kind of private fields that you can use inside the function, the methods, but not outside. And let me have something more complicated here.
You wouldn't be able to define them as CPDEF.
We can try, but it doesn't allow. So the CDEF and the CPDEF applies only for functions because it instructs Cython to generate two versions. One that you are able to access from Python and one that you are able to access from Cython, which is the more optimized one.
Okay.
Okay, so here I have again the rectangle and I create another class, which is a collection of rectangles, more or less. So here I have a Python list with CDEF. So these objects that we are very familiar with when we are programming in Python, like a list, you can use them inside your Cython code. Of course, this as a CDEF, you will not be able to access outside. You will only be able to access with self rectangles from inside. So I compile this and I just tell this to create a list of 100,000 random rectangles. It's very fast since it's C, and I can calculate the total area for that. So you see here that objects like list are available inside Cython, and you can use them like you would use from Python with append and everything. And let me go a little bit into a little low-level stuff from C. So whoever is programming in C and is familiar with C, you know that C is not very helpful in terms of memory handling for you. You have to do everything manually. While in Python, whatever, it has a garbage collector, so it handles the memory deallocation for you if something is no longer used. And here, I will show you how I can create type of range vector in Cython as a Cython class using the malloc and the free from Cython, which actually are the malloc and free that are defined, that are inside the standard library of C. So you can access the standard library of C from Cython by importing libc stdlib, and from there I C import malloc and free. And here I have the special method cinit, which is more or less the constructor. Here I have the get item, which is the special method from Python, which allows you to do indexing. And here I have the destructor, which calls free of the data that I have allocated here. So here, whoever is familiar with C, this is a malloc. I use the size of the vector and the size of int. So this is what you would use in C as well. And here I cast this to a pointer to an integer. Here is how Cython, with these symbols, you indicate that you want to do a typecasting. So I want to convert to cast what is returned by malloc, which is a void pointer, and to an integer pointer, so that I can assign it to self data, which I said that it's a pointer to integer. So let's see how this works. So I can create my range like that. And as you can see, I can have my range with an index like a normal Python object, like a list or whatever. So this is provided to me by the get item. So again, here I have the dialog that if I was in Python, I will not have to do, because Python does the deallocation for me. But here, since I'm programming in a lower level and I manually handle the memory with malloc, I have to deallocate it with free when this object is deallocated. Any questions?
There is a question on the chat.
Yeah.
If I use cdef list as data type, which kind of container gets mapped into C?
If I use the list here,
cdef list as data type.
So this is what Cython uses in the lower level to be able to use it as a Python list. So it's more or less a Python list, but in Cython terms. So this is so that you can use all the methods that the list provides, like append or indexing or whatever.
But in terms of C, this has to be mapped to some sort of data type, right? So like a vector or a list or an array or something.
I know what I mean. Yeah. So here you can add whatever you would like to it. So you see here, I could add a normal object, a Cython object, like anything. So I will show you how this looks like when you want to specify a proper typed list. So here it's a Python list, more or less. It's an implementation of the Python list which accepts whatever you throw at it. So to answer your question on that, so you can interact with the C++ standard library instead of the C library.
Can you?
Yeah.
Can you, on all these double underscores and function definition?
Yeah. So this is something that Python calls dunder. So there are a special kind of methods or function that Python knows and calls for you without you having to explicitly say that I want to call it. So here, when I use the sci-range vector, it knew how to construct and then call the C init for me with the start and the end that I passed. And here, when I do the indexing, I didn't say dot get item, but when I use the indexing here, it knows that I'm telling Python that it should go really and look for the get item method. So it's
so these predefined functions that have to be.
Python has this stuff already, yeah. So it knows that if you mean that you want to do indexing, you have to provide a get item method. And that is why it has the double underscores before and after, because these methods are special for Python.
And if you just leave out this def get item until the return, and then you say you try to let it run, it will tell you there's a get item missing, or?
What do you mean? So if I delete this here?
Exactly. 3 lines. Oh, 4 lines.
It says object is not subscriptable. So it searched for the get item, but it couldn't find.
It's a little, okay. It's a little cryptic, but it's there.
Yeah, so for normal function, you don't use the double underscore because those are meant for Python to handle specially. Okay, so time is running out, so let me go into that and finish. So we can use, as I said, the C++ standard template library, which offers some containers, which you can use. You pass also the type that the container accepts. So you see here that I imported now from libcpp vector. I imported the vector. Now I have to pass, as before with the, you saw that we passed some arguments for Cython to pass to the C compiler. Now we have to tell Cython explicitly that this is it has to generate C++ code for that. Otherwise, it will not be able to use this. So now I have a class sci-range vector, and here it's a vector of ints. The good thing with that is that Cython knows how to map more or less standard container types to the corresponding Python type that is associated or that it's convenient for you to use from within Python. So if I do this, you see that I can use the Python v1 here, or probably I could use also, I don't know, no. So I cannot use the sum, but I could pass it whenever Cython asks me for a list. And this again, I can create a sci-range, I call it here, which you have a vector of integer and have like that. So now if I try to do v2, for example, equals 2, object does not support item assignment. So you see here, it doesn't allow me because I have only the get item and I don't have the set item. So here is how you can use from the standard template library something like the vector. Also, there are additional types that you can use. So let me just show you what I meant with the mapping between the C++ containers and Python. So you see here, I return a vector of integer, which is a C++ object. But when I return it to Python, Python interprets it as a Python list, which is more or less the corresponding container type of the vector of integers in terms of Python. So here I can actually do some here. So does this cover your question about the how I can more or less have templated or restrictions on the list I pass?
Yes, thank you very much.
So here also keep in mind that as far as I return this object in Python space, I can do something like that. Like I can assign whatever. Or a float. And then you see. So I'm outside the protection that the C++ code gives me. So because this is converted to a list and I'm outside of the Cython realm, I don't have this protection anymore. So any questions?
There's a question in the chat. Which C++ compiler is used by default when compiling code generated by Cython?
So Cython will, I think it will use the one that is referred to by CC, by this CC, and this CC is for C++, and no, it's not an actual. So this CC is for C++, and this CC would be for the C compiler. So you can tell Cython to use a different compiler if you point it to different CC and CC every time. But this you will have to do probably outside of here, or specify somehow before running the Python magic, because otherwise the Jupyter magic, because otherwise it will take what is already defined for the C++ compiler. Also, I have here a link to the additional stuff that you can access from C++ standard library. You have like an ordered map here, and it's the hash maps that, or whatever C++ provides. And here, this is mapped to a Python dictionary when you return it. So you can have all that. So to conclude again, tomorrow we will see some more Pythonic ways to optimize and accelerate the code. But Cython is really good if you want to interact with an already defined, already tested C library. I have some things here, the wrapping C and wrapping C++, which we will see tomorrow. So I have in the README how you can compile those. But I wanted today to have your focus on the actual Cython and not how you compile the code. So that's why I wanted to use this Cython/Jupyter magic. So any other question? Otherwise, we can head for a break.
This is a question in the chat that I missed. I just realized it is above, but I don't know in which point. It says, what would be the simplest way of making a square.x accessible from within Python? But that was some time ago.
square.x.
Accessible within Python.
So you mean so does any who asked this can
Well,
they-
this was earlier when you were talking about the psi rectangle, and you showed that the object.x attribute was not accessible.
Yeah.
Yeah, so just wondering if there was some means of making it accessible, because it's totally foreseeable that you'd want to be able to access it.
Yeah, so you should make more or less a function for that. Or basically, I don't know if you can access it. I don't think you can access it like without having. So you have to predefine more or less your actual fields here, which are then not accessible outside. So
and so would a property decorator work here or not?
I'm not sure, because then it might be something that Cython does not like, but you can try something like, for example, I don't know if I can use some property or whatever. I don't know if it's possible to use outside. Let's see.
I mean, it seems natural that it wouldn't be, but it's sort of like if there was some way.
I don't know. So, yeah. Dev, no. Say the flow, not declare cpdef. So, yeah.
The constructor is cpdef. So the first line of the class, no, above the double XY cpdef.
Yeah, sorry. So, yeah, it could work. Let's see. But now I guess it will do a. It's not, so that we don't have the problem. You can do it like that with the property. But then again, I don't know if this is going to work with cpdef. So yeah, if you want to do it cpdef, no, because here you are completely in Python mode. So you can do it with a decorator, but only if it's a def.
Great, thanks.
Any other question? If not, Rafael, what time do we return?
Okay, in 15 minutes, 10 to 3, we can meet for F2Py and CFFI.
Okay. Otherwise, whatever question you have throughout the day, we can discuss also after. Okay.
Sorry, maybe I can I have a question?
Yeah.
So you haven't mentioned using NumPy with Cython too much. I always wondered what's the difference between so I see some codes just importing NumPy from Python in Cython scripts, and then there's maybe afterwards there's C import NumPy. What's the difference? Why is that useful?
Okay, so this is a real something that is more complicated. So the C import stuff are the stuff that you need to be available here at compile time. So the C import are the things that you are going to use during compilation. So whatever you want to use from inside a Cython function, but from the side, from the C realm, you have to do it with C import. So you see things that are 100% C, like the malloc or the free, I do it with C import, because these are really C functions. So they are not defined from Python, and that's why you cannot call malloc and free from, I cannot import and use it in a normal Python function. So this is something more complicated, and has to do more when you start developing wrappers inside of libraries. So if I go to something like wrapping C, for example, here you have some stuff that we will talk about tomorrow. So this is something that is really defined in C, and then I have to somehow use it from Python, and I do import. But if I want this to be checked and at compile time, it has to be done with C import. So from Cython, I guess I have seen the one that you are referring to. So NumPy has an interface to working with Cython. So you do C import for that. I don't know if this covered your question.
Okay, so as far as I understood, the C import at NumPy, you import in the part of NumPy that it's already C, and why do you need the other simple import NumPy without a C import NumPy?
So the import is for the things that are exposed in the Python level. So if you have an array and you want to do an array, a NumPy array, for that you need the proper import. But for things that are at the C level and that are not accessible from Python, you have to somehow import them with the C import. So if it's something like cdef that you want to use from inside, this you import with C import. I cannot import the cdef with a normal import.
Okay, so if I call NumPy imported without the C import, so if I create an array inside a function, let's say that it's that should be compiled, then it will never compile into proper C, since I'm importing NumPy without the C import. And so say I need to create an array, right? So with NumPy, for that I need the normal import, and therefore whatever function that uses that NumPy version will never be compiled entirely in C. There will always be a call to Python somehow.
There will be some interaction, but again, NumPy is written in C, more or less, and it interfaces with some Fortran stuff. So again, this will be an optimized version, but there will be some interfacing with Python.
Okay.
So, for example, from outside, I cannot, from a typical cell, without it being Cython, I cannot do something like that. You see?
Yeah, no, that's clear.
So the C import is for things that I want to import that are in the C domain. So I want to interact with it in the C domain. Like I can access it when I'm writing Cython code. I cannot access it outside, because the Cython code will be compiled the time. So you see here that this was done in a single step, while if we do it ourselves, it requires the normal C steps like compile, link. So this here, when I press this, I do the compilation actually. So here, there is no Python function that is called, no Python thing that is called vector. And also here, it even doesn't find the libcpp because it's supposed to be accessible from Cython code. So all this stuff here, whatever you see with C import, will be treated at compile time. So it's a little bit, I don't know, if you are used with interfacing with Cython and with C code and Python, then this is really important. I will look into it in more detail.
Okay.
I will let you know tomorrow also, because I know exactly where to look, because I have been looking at it, but I'm not 100% sure of the. I mean, I know that the one you import from C and the other from Python, but the difference is a little bit vague, especially for modules that provide both Cython interfaces and Python ones, like NumPy.
Okay, thank you.
Any other question? No, I guess you can ask us afterward. So thank you.
Okay, thank you, Theo. Then let's meet then at 3. Let's take a 15 minutes break, which is the normal schedule that we had.
Okay.
And we meet at 3. Okay, see you.
Now we are going to have a look to interface, how to do Python interfaces to Fortran 90 and to C. For that, we're going to start with the Fortran. So let's go all to the F2Py folder. And here we are not going to do notebooks. We're going to work in the terminal. So you can use the terminal here as in the morning, new terminal. And remember doing this thing. I will paste it again in the general channel. So to activate the environment, okay? It was just to source this, just to copy and paste the command I put. Okay, so we can start. So we can go here first to distance F90, and in the folder there is a README that you can open. It's a Markdown. You can open it with right click and then open with Markdown preview. Just don't double click it because otherwise it's going to be in raw Markdown. And in Markdown preview, you will see something like this, and there you can find all the instructions for this tutorial. So in this tutorial, we're going to use F2Py, which F2Py is a program that comes with NumPy that is used to generate the binding. So given a Fortran 90 code, you will run it with F2Py, and you will build it with F2Py, let's say, and it is going to generate a C wrapper for Fortran, and from the C wrapper, it is going to use it's going to make a library that we can later import in NumPy. Okay, and like this, we can do. We have a lot of. It really opens a lot of possibilities because, like in this case, for instance, the city block. Remember, the last thing in the morning session was the city block. To do city block distance matrix, we cannot apply the same trick, and that we did with the Euclidean one. So we have to keep trying other solutions because NumPy is not a really good solution for this particular function, and so we can use Cython, of course, or tomorrow you will learn about NumPy. But this one is a very simple option if you know some basic Fortran. You just can write your function in Fortran and you will get a pretty fast implementation of the city block. Here we're going to do that, and we're going to compare it with an implementation of the city block distance matrix that is on SciPy. So SciPy spatial distance, it has inside. But this one, although this is a very most of the code in SciPy and NumPy has a good implementation, it's not multi-threaded. So it's not going to be too fast, and we're going to run some comparisons, and we're going to see how faster we can go doing these kind of things for almost not too much work. Okay, so we start. We have this function that we tried to do it in NumPy, was not fast enough. We tried our favorite libraries; they are not, they don't really help. Say, okay, let's do it in Fortran. Or if you like Fortran, you go directly to Fortran, of course. So here, we're not going to stop too much here in the program, but even if you don't know, it's easy to read. You have a subroutine. A subroutine is roughly similar to a function. It just, it doesn't return anything. And so we call it city block distance matrix, and we pass the arguments that we need. So x and y, like we did in the Euclidean trick and Euclidean broadcast. So these are the vectors of these matrices with the row vectors. Okay, but we are going to loop over them. We're not going to do any vectorial thing like in NumPy. So we're going to do a very basic loop here. And so to loop here in Fortran, we will need the sizes of x and y. So we pass the number of samples, I call the number of rows, and the number of features, I call the size of every row, no? The size of a vector. And finally, since this thing, the subroutine doesn't return anything, we just we need to put a variable, which is where the data is going to be saved. Okay. And these are some definitions in Fortran that this says what is what. This is the sizes. This is important because we need to match this with how we're going to read the data in NumPy later when we do the binding. Okay. So we define here, we have double precision for X, Y. So this is something that you can read, that you can pair it with NumPy arrays with dtype float64, which is the default. Okay. We have some ints and again another double precision. So this with X, Y, and R, we're going to pair them with NumPy arrays later. Okay. And here the loop is very simple. Loops over the two list of vectors, and inside of this loop we just apply we compute the city block distance, which is the abs of the difference. Okay. And we have this temp thing and this temp variable, and at the end we pass it to R, to the solution. Okay. And we also add here some OpenMP directives. So we are going to do a multi-threaded implementation. And that's it. This is our implementation. Now, if you come here, you have in the README, there is this command to build it. The command to build it will use the setup.py. Okay. Okay, we can build it first, and then you see what happens, and then we go to the setup.py. So you do setup.py build ext. This is in place. It's just to have it here in this folder, but build ext is enough. So we build it. You see here GCC. Well, it's too fast, but. So you see here, you see GCC and well, it's a lot. I will explain later. So if you do ls, we got this build, which is a temporary directory, and we got this metrics, and this in metrics is where the things that we wanted are there. So we built these two libraries. One is for the city block, and the other one is for the Euclidean. We also implemented in Fortran just to compare with NumPy. And so if you look in this build, you will see so there are Fortran F2Py wrappers. There is C code. The same for both of them, and so what these things are just a way to communicate Python with Fortran, because Python doesn't have interface directly to Fortran, so it is done through C, in particular through this header file python.h, which has all the Python API to deal with, to communicate with C, okay? But you don't care about these things. It's just created by F2Py, and it's just huge, long code. So we don't look at it. What we care is what we got here, the metrics. And okay, so you know already what is happening. And let's see how we build this one. So to build, we use NumPy. So we created this top.py, and for that we use the numpy.thisutils.core, and from there we have this extension. An extension is a set of Fortran sources, and setup is something that we're going to run later. And the idea is you have to create one extension per package that we're going to build. And package is one of these libraries, okay? So in this case, we just load here, And we define some compiler flags and some linker flags, and this is for F2Py just to print more stuff. We specify the language, and I don't know if there is support for Fortran 77, but I think most of the support is F90 at least. I don't know if Fortran 77 is well supported, but anyway. And so those are just variables with compiler options. And we create the extensions. And the extensions is the libraries that we're going to compile. So in this case, we specify the name. We call it EDM. So remember here that we call it EDM is what was produced. We put the source. In this case, it's Euclidean. Where is the Euclidean distance matrix implemented? And we pass all the options. Extra F90, extra F90 compile. So these things we pass it here. This one probably is not needed, but as a template, you can reuse it. And options, language, so everything. So that's it. You do the same for the other one that you want for CityBlock. And at the end, the other thing that you loaded was imported was setup. Oops, sorry. So that's it. You say setup, the name of the package that are going to be this metrics that I showed you before, and there you include the two extensions, and that's it. That's it, it's already, and then you run this Python setup build, and that's it. You got it done already. And so in this example, it's very simple. But if you want to do something like this for your work, you just can copy this example and modify the bit, change the Fortran code and change the setup, and that's it. It's very clear and very simple. And then so now how to use it? Let's open this one, CityBlock. You can import directly the function. So this function, CityBlock distance name, is the name that we gave here. CityBlock distance matrix, sorry, not CityBlock distance matrix. So you say for matrix, CBDM, CityBlock distance matrix, import this one. And that's it. You have this function. Now this function is a bit special because this is the Fortran function. So what you are going to pass to this function is a bit different of normally, well, not too different, but you have to do some particular things to work with it. So the first thing is that it won't return anything. You will pass a variable, and it will write in this variable. Remember that there was the thing with the subroutine, and it will save the CityBlock distance matrix in this variable. So you have to create the variable first, and you can create it like this using NumPy empty. It's an empty array. It's an array that is not initialized. It just fills a block of memory, allocated a block of memory with certain shape, and that's it. There is not there are no values initialized inside. And you have to specify that the order in which you want to read this block is in Fortran, because remember that by default it was in C. There was a row major. So now since we are working in Fortran and the order in Fortran is swapped, is transposed compared to C, you have to say is Fortran, okay? And the other thing is, remember that we did this when we generate the data, it was rows of the vectors of our vectors were in rows, not in columns. So here this function, since it is a Fortran function, it is expecting these values to be also transposed. So you have to pass the transposed, okay? And you pass the you have to pass the sizes, of course, because your function the subroutine is expecting it. And that's it. The rest of the program, you treat with it, you deal with it normal. Even this this variable that is in order Fortran, this is no NumPy worries about it. You don't. You treat it as normal. NumPy knows that he has to read it different, but you don't care. Okay. And so in this example, we're going to run it now. We also import this cdist from SciPy, and we're going to compare. So, we can run it. So ours took 0.43 seconds only, and cdist took 3.65, almost 4 seconds, and they both give the same value. Okay, we can try also EDM, Euclid distance matrix. Pretty much the same time, and yeah, and NumPy takes also much more. Just look here that we put here a lot of 12,000. No? It's a large array, and the values are fine. And that's it. This is all that you want to do. That you need to do to get this thing working. Is I find it is pretty simple, and I can really help you in situations where something is hard to implement or not possible to implement properly doing vectorization in NumPy. And there is another point here. This is like the basics, the basic thing you can do, the most basic thing you can do. But Fortran F2Py give you also some support for more Pythonic functions from Fortran, but it's a bit. It depends on F2Py guessing things from the way you define your Fortran function, your subroutine. And so I want to show you the two examples, because the first one, the one we did, is just by hand. So you decide what to do. You put you create the empty array at the beginning. You put the sizes, but you can do something like this now, and F2Py will guess things for you. So now, we have the same, until this point is the same definition of the function, x, y, the sizes, and r. R is going to be the distance, is going to be populated here, and you're going to get it from here, okay? But now, compared to before, we define the arguments more specific. Now we don't put that is a bidimensional array of unknown size. Instead, we put the sizes, and we put everything very specific. So x, we say which size is going to have, and r, same for y, and same for r. And we also we put here the intent, that we say that these two are input, these two are inputs, and this one is going to be an output. The rest is the same. But now with this information, F2Py can guess how this function is going to be used in Python. And so you do here the same. You no, let me show you city blocks. It's shorter. City block. you imported the same, but now you don't have to do this thing where you have to pass to create first the array and pass it and populate it inside of the function and give it back. Here, when you load it, F2Py is going to know, is going to infer how you're going to use the function because of the intent in out that you give and because of the shape. And it will be smart enough so you can pass only the input, as we did before with the Euclidean trick and Euclidean broadcasts, and it will infer that the rest, the sizes, are the sizes and R and the distance matrix are optional arguments. And since you said that the distance matrix is an out, intent out, it's going to make the function to return it. And then you can do something like this, which is a bit more Pythonic. And that's it. From the setup.py, it looks exactly the same. It doesn't require anything else. It's just mostly how you write your Fortran code. In general, these kind of things, when it depends on some wrapper or like F2Py, some kind of program guessing things from you, you may find undesired results. But in that case, you know already what to do. It will be what we did before, no? Just everything by hand. You pass empty arrays and everything should be fine. Here, I won't give you time to play too much with it because I think not everybody is interested in this part with writing Fortran code. But here I put an exercise as a homework. There are some instructions here that you have to implement a matrix multiplication. So here you have to add the missing parts. So define the arguments and add here the arguments. And there are two questions. One, to do it in double precision and to do it in single precision. So you have to keep in mind that if you do it when you change double precision to something else, you will have to change something in NumPy, so you read the memory properly. Otherwise, you may have problem reading the block of memory. Okay, but that's it. If some of you are interested in this, you can do it as a homework, and we discuss it in the chat any of these days. So, are there questions?
I have a question, but maybe a bit more philosophical.
Sure.
I mean, in the beginning, in the morning, you showed that, well, you were really making clear that you cannot use any kind of loop structure in Python because it's way too slow. It's an interpreted language. And that's why you use NumPy. But in order to be able to use NumPy, you have to vectorize everything. That means you have to do some constructs that may not be so easy to view from the very beginning with this broadcasting stuff and so on. And you showed that you can get quite quick this way, but if you do it in a very simple Fortran fashion, you're still 10 times as quick. That's the impression that I get. And looking at the Fortran code, it wasn't even very much optimized.
Yeah.
It was standard.
Yeah, yeah.
My question would then be, why does one want to deal with NumPy in the first place if one can have it so much faster and easier this way with a Fortran code that you bind into Python?
Well, the easier part that you see is not for me. I don't agree because it's not. It really
is still not nearly as fast as self-written Fortran would think.
I'm sorry, I missed a part. I think you were breaking a bit. I'm sorry, I cannot hear.
Did you get me?
No.
No, obviously. Okay.
Yes, I'm okay. Okay. I'm sorry. Could you repeat? I didn't hear the last part. Okay, I think something is happening. Maybe if there are no more questions, we can move to the C interface. And yeah, I just wrote to Dirk because it seems that he has a connection problem. One important point here is that in general this should be used for compute, yeah, for CPU intensive parts. You shouldn't do the whole code or very long parts of code in terms of lines in the in Fortran. It would be yeah, something like here we did. Let's say that part of our code requires to compute the distance matrix, and we put it we put it in a function, and this function we do it in Fortran or in C, as we're going to see now, but not like big pieces of code together as a single, yeah, sort of a monolith of Fortran. Okay. So let's have a look now quickly to CFFI. So now that you saw this one, how it works, the other one, this one is going to be pretty similar. Okay, so there are two different ways of using it. I'm sorry, by the way, here now we go to CFFI. And here you can open this one with the Markdown preview, and all the options are here. So there are two different ways of using CFFI. CFFI is it creates bindings to C code, but can be to a given code, source code, or to a given C library. Okay, so these are the two ways of you can do bindings. And by the way, CFFI stands for C Foreign Function Interface. Okay, and so we're going to start with the code version. So the code version is pretty similar to what we saw before. We have this city block here. We have a definition similar to what we did in Fortran. So two inputs. The output would be R, and the sizes. And then we have some OpenMPI directives wrapping these for loops. And the for loops, they go over the two arrays, and then one inside that does the city block distance per vector. Okay. So we have this code, and we have a header file just with the definition of the function. And that's it. So now with CFFI, there is not an F2Py executable or this setup .py with these tools from NumPy. So it has a different way of doing it, but it's not too different in practice. So we import the CFFI module, and we create this FFI object from it, and we read the header file, and we read the C function. So we put it here, and from this FFI we use set source, and set source we specify the thing that we want to build. So we build we call the library that we're going to create underscore city block, because we want, and we pass here the code. This is that we read here. So we read in a variable, and this one, sorry, this one we read it in a cdef FFI cdef function. So we pass all the definitions from the header file to the FFI objects itself. And so at this point, FFI has the header, so the definition, has the code, and we pass some arguments for building and some arguments for linking, and then we say FFI compile, and that's it. We do now Python, and that's it. So in this case, I am building with GCC. This is building, yeah. But I think if you do something like this, you may be able to build, yeah, you can build with GCC, okay? And GCC here is only used as a linker, okay? And let's see if it works. So it creates this library that has the code. So if you look to the symbols of the library, you see that somewhere inside is defined our function, and it has a lot of Python symbols inside that make it possible to import it on Python. And it also it generates code for wrapping. And here you see again the Python.h, okay, the Python interface to C, and just very large codes for wrappers. And how we use it. So so this part is for comparison, it's NumPy. We import again CFFI, and we import the FFI from it. And here, the library we imported is not exactly like in Fortran. We do from cityblock.lib, we import the things that we have defined on our C code, okay? And the way we use it is a bit more ugly than the F2Py that does a better wrapping, but it's not too difficult in total. So you know this step already. You generate the empty array. In this case, the order of the data buffer is C, so we don't have to change it. It's by default is C. And we create this FFI object, same as we did before. But now the function is not expecting is not receiving NumPy arrays as we did in the other one. No? In the other one in Fortran, we pass just the transpose. So now we have to pass the data buffer itself. Okay, and so here what we do is FFI cast, and we convert the data buffer, which is xctypes.data, so it's the block of memory. We cast it as double, which is the type we define in our C code for X, and we do the same for R. And we can call the function, and everything that is saved, that is produced, the result is stored here in RC. Okay, and that's it. This part looks a bit ugly, but it's all in all is quite simple. And the thing, if you're doing implementation like this for a package, you can very easily wrap it in a Fortran function, so that you create a Fortran function, city distance matrix, where you pass x and y, and so samples and features. The sizes can be created inside of the function. This can be added inside of the function, and at the end you calculate this and you return RC. And no, sorry, you return R. I'm sorry, I think I flew over a very important step, which is RC is what you pass. So you pass the block of memory, and the C function is going to write in this block of memory, okay? But this RC, you cannot use it in the rest of your, after, you know, in your NumPy code, in your Python. This is just a block of memory. But when you change this, when the function change this block of memory, the content of R here is going to change. So even if this R, you never use it, you never call it, after this is run, R is initialized with the distance matrix. Okay, so you wouldn't use this one. You would use R. Okay, that's a very important thing I just didn't say. And we can try it. And again, we get a very simple, a very quick implementation, and I don't think it's too much work. And that's it. It's very simple. And the second example is pretty much the same. The only difference is that we won't pass the code. Instead, we are going to build the code ourselves, because we're going to pass a library. Okay, that this one you may use it if you have a library that already has been given to you, and you have a function inside that you can use, that you need to use. So you can interact from Python with this library using this way of generating code. And the only thing that you need to do is know is the definition. That the definition, so the header is this, because you will need, of course, all the types and know how the function works. So so in this case, we read only the header. We pass it to the FFI CDEF. So this part is the same of the other one. And now when we set source, we put the name, but instead of the code, we only give this include. That it means, okay, use this one for this library. If you don't put it, it would work again. It would work too. So you can do something like this. But you may get a compiler warning, because there is no definition of this in your library. Okay, The rest is the same, except so here you have to pass where the library is, and here the name of the library. Okay, and the rest is just compiled. And so to build it, we can create. We have this make file. So the make file is going to create the library. So if we do make lib, so we have this library. So at this point, we can just throw this. We don't care for the source. And here, the only thing I do is just to run Python CF, the same thing we did before, and that's it. I just put it in a make file to make it easier. So we can do make pylib. It's going to run the whole thing, and that's it. It's going to generate the code and create the library. And now, if you look here, this library is looking to libctblock.so. So this one, our library, our code that is in a library, but it says not found. So to make it visible, you need to put this library somewhere where the LD library path is going to look at. So for that, you can do this, export LD library path to this directory where you are now. Now, when you do LDD, you will see that he knows where the library is. Okay, and we can run test ctblock, and that's it. Yeah, and the way you use it now is just exactly the same as before. The only thing that changes is how you compile it. And all this thing that I just talked is here in the readmes. You can see it, and there are some explanations. And that's it for CFFI. Same thing as in Fortran. This one you can use it for bits of code, for intensive parts of your code that is hard to implement in Python. You just can very easily implement it in C if you don't find any other solution that you prefer. And here as a homework, I put as an exercise how to create a wrapper. So a wrapper is a function. So define a function that you pass x, y, and it will use our C function to inside. So it will behave like this. Something that you do that you call ctblock xx, and it will return the distance matrix. Okay, and so that's it for today. If there are questions, okay. If not, I think we can finish today here. And thank you for the attention. Thank you for coming. And tomorrow you will go to be all the day with Theo, and you will learn about NumPy and how to use GPUs from Python. Okay, I think that's it. See you tomorrow. Bye.